thank you all very much for being here, and thanks, Takeda-sensei, for giving me this prestigious opportunity to present here today. And okay, the title of this talk is an intentional pun. So the envelopes we are going to talk about, we have seen some of them in the previous presentations. And thanks to that, actually, I will give some basic needed material for granted. So I will just give some definitions and trust that you follow the previous presentation. So I will actually follow a bit of an unconventional structure. So this is the, I don't know if you can see the, probably should have uncovered everything. Anyway, I've divided my talk into three sections. Actually, let me put the timer so that, okay. Into three main sections. And in the first section, I will talk about the Moro envelope. Okay, the Moro envelope, we've seen it already. And I will just repeat a bunch of known stuff, and the rest of the things will be totally useless. Okay, but the idea why I'm dealing with the Moro envelope is that all the things that I do in this first section sort of carry over and generalize to more complex envelopes, which have more, let's say, practical utility. And we will see a sort of a flavor of this in the second part of the talk, where I will talk about structural problems. And then in the last part, I will try to provide a theory that embraces all these, all the possible envelopes. And it also gives you a way to create your own to some extent. So I will start very abruptly. So in general, we are considering minimization problems. So it is not as general as Harold's talk this morning, where you had more inclusion problems. I will focus simply on minimization problems. But so far, I'm not making any assumption on this cost function phi. So for me, this function is simply, except from the standard working assumptions, which are properness and lower semi-continuity. And of course, since you're minimizing it, I'm just assuming it to be lower bounded. Otherwise, it doesn't make much sense to minimize. And we will add some structure later on. And throughout the entire presentation, these will be the two guys that we will be mostly talking about. So the proximal mapping, which is, the result of this, if you want, parametric minimization. So you take your cost function phi and you add a quadratic term centered at some point of reference, and the set of minimizers is the proximal mapping. And since our function is non-convex, so if my function was convex, then this would be a strongly convex problem, and there will be a unique solution. In general, if this function is non-convex, you may have more than one minimizers. And therefore, this prox is not a function, but is a so-called set-valued function. So this double arrow indicates that it is a point-to-set map. Instead, if we consider the value function, so instead of taking the minimizers, we take the minimum value, what you obtain is the so-called Moro envelope, which is the first and prototypical example of envelope that we're going to see throughout. And projection and envelope, respectively, are a generalization of, proximal mapping and envelope are respectively a generalization of the projection. So if your phi is the so-called indicator function, which is 0 on some set and infinity outside, then basically you're simply finding the closest point to x bar inside that set. And this gives you the projection, and the envelope reduces instead to the square distance and scale from some parameter. Now, just to start smoothly, let's say, and pun intended, I will assume that our function phi is convex just for this slide, and then we will abandon this setting completely. But just to see what we have in the convex case that we lose in the non-convex world. But the point that I want to make in the rest of the talk is that we don't lose much in the non-convex case. So all the things that we need are preserved. Okay? So if this function phi is convex, then also the envelope will be convex. This is a standard result. Very importantly, the envelope, so the so-called the Moro envelope of this function will be even differentiable. And we have a close, we have this expression for the gradient, which is identity minus the prox divided by gamma. And in this case, as I was saying before, this prox is actually in the convex case, this prox is not a point-to-set mapping, it's actually a point-to-point mapping. And you can also show that the gradient, the prox is Lipschitz, and as a result, also the gradient is Lipschitz, and the modulus of is 1 over gamma. And a very important property of envelope functions in general is that, of the Moro envelope, is that the Moro envelope shares minimizers and minima, let's say minimum or infimum, with the original function. So by doing this, so by noticing this, I have created a differentiable function which shares minimizers and with the original function. This means that my original convex but possibly non-smooth minimization problem has been translated into a smooth minimization problem. Okay, and since this has this function has Lipschitz gradient, the most standard way of the classical method for minimizing a Lipschitz differentiable function is the gradient method, where we have a step size that I call tau here, which is, we know, in order to guarantee convergence, it has to be between 0 and twice the inverse of the Lipschitz modulus. So I have this tau ranging in 2 over gamma. But now if I plug this formula for the gradient in there, what I obtain is simply a so-called relaxed version of the proximal point algorithm. So proximal point algorithm means simply fixed point iteration of these prox. So when lambda is equal to 1, or if you want, when tau is equal to gamma, I guess, only this guy remains. But in general, I have a sort of averaging or over-averaging taking place with respect to the current ether. And with no, and I know from, since lambda is tau over gamma and ranges in between 0 and 2, I have that for every choice of this parameter lambda, I have that this algorithm converges, in fact, to minimizers because of global minimizers because of convexity. Now, there is no need whatsoever to use this gradient descent interpretation in order to analyze the relaxed proximal point method. You can also show that this converges by even in a more general setting. But the point that I want to make here is that this interpretation allows us to improve this algorithm here, this, let's say, abstract algorithm, if you want, with the non-fast smooth minimization techniques. And so, for instance, you can consider Nesterov acceleration, or you can do Newton type, I don't know, you can do quasi-Newton type methods, okay? So, okay, so this was all for the convex case. Now we will abandon it completely, and we will go back to the original, to our original problem, in which our function phi is just assumed to be proper and lower semi-continuous. And if I want to restudy this proximal point algorithm, so these fixed point iterations of this proximal operator, of course I have to include, I cannot have an equal sign anymore, but I will have an inclusion. So then again, I may have many, this prox operator is set valued, but whatever point I choose, in some sense, this algorithm will work. Now, as I was saying at the beginning, this entire first section is only conceptual because in general, if you have a practical problem, then the practical cost, you will never be able to compute the proximal mapping, okay? So usually computing the proximal mapping is as hard as solving the original problem, okay? But so we will fix that later, hopefully. But, and most importantly, in any case, even if this is only theoretical for the moment being, the proximal mapping and the Moro envelope are really structural for all, for a wide class of algorithms called proximal algorithms. So just to give a quick look at what properties we can exploit in this generality. So the proximal mapping, again, is now set value, so we cannot talk about continuity in the classical sense, but it satisfies a set valued continuity. So if you take the graph of this operator, the graph is a closed subset in Rn times Rn, which is also known as outer semi-continuity. So, okay, and this is the regularity of the proximal mapping. Then we have also, the necessary condition defining this point xk plus 1 in the minimization problem defining the prox tells you that this condition must be satisfied. And this partial with the hat is the regular subdifferential. That is the Frechet subdifferential. Now, in the convex case, there is no distinction between limiting, Frechet, convex subdifferential all the same. And in fact, this subdifferential property is actually a characterization of xk plus 1 being the prox of xk. In the non-convex case, we only have that this is a necessary condition, but it's not sufficient. But okay, it suffices for our purposes. And the last very two important things, that it's very easy to show that if you do one proximal map iteration, then the cost decreases. So the cost decreases along these iterations. Not only decreases, but it decreases sufficiently. What do I mean by that? It decreases by a quantity which is proportional to the fixed point residual. And now, since our function is lower bounded, then we can use, we can employ our cost phi as a so-called merit function, as a Lyapunov function. What do I mean by that? Meaning that if x star is a limit of the sequence, I have that x star will belong to the prox of x star itself. And because of this, so x star minus x star, all these points become x star, which means that 0 belongs to the regular subdifferential. And we should also appreciate the fact that we never involve the limits. So usually when we talk about, we have subdifferential inclusions and we take limits, what we need to use is the limit differential. But because of the regularity property of the prox, everything, we don't need to involve the limit differential. We can directly know that it holds for the regular subdifferential. In the convex case, we could show that these kind of iterations make sense for any parameter lambda ranges in 0, 2. And in this case, instead, we only analyze the case lambda equal to 1. Okay, so plain proximal point iteration. And of course, in this case, the cost, if we add these relaxation terms, the cost will no longer be meaningful. Also because iterates may be outside the domain. So phi can be infinite valued. So we don't have, first of all, we don't have any such condition. And in any case, it may be infinite valued. But okay, it's very easy to show that if instead you try to reason in terms of the envelope, the same way as in the convex case, you get exactly the same inequality that you were getting in the convex case, okay? So the envelope has same infimum as the original function, so this means that I can use the envelope as merit function. And by, by the same reasoning as before, you can show that any limit point is regular again. Now, this inequality, you can get it with you can do some in 2 lines of proof. There is nothing special about it, but I want to now show that there is something more than meets the eye in this inequality, and which is very tightly connected to the convex case. So I would like to recover a sort of gradient descent interpretation, but if I try to do that with with the regular subdifferential, I really can't, because I still have a sort of relation in terms of the subdifferential of the envelope and this so-called fixed point residual scaled. The problem is that here I have an inclusion now, I don't have an equality, which means that I cannot, in general, see the proximal point algorithm as a subgradient method or a generalized gradient method on the envelope. And this is not a matter that shows the regular subdifferential. Even for the limiting subdifferential, this doesn't work. Okay, and okay, I can give you a simple function as an example. Okay, I don't want to go into detail here, but trust me that in this case, 0 is actually a fixed point for the proximal map, but you cannot see as a subgradient descent or limiting subgradient descent on the envelope. Anyway, what we do know, however, is that for minus the envelope, we have an important subdifferential equality, identity, okay? And this is not surprising because the envelope is the result of a marginal minimization, which makes the envelope well behaved from above, okay? And I will explain what I mean in 1 second. For the moment being, suffice it to say that we know that our is the convex hull, okay? So let's say the subgradient of minus the envelope is the convex hull of this thing here. And so let's say instead of having a subgradient descent on the envelope, what we can interpret the proximal point algorithm as is a subgradient ascent on minus the envelope, okay? So this is actually more than we need because here I'm taking a convex hull. So I'm not, I'm a bit, this is more general if you want, but the proximal point algorithm is a special case of, so corresponds to a special, to some selection of subgradients in here. And okay, this may look useless, but so let me formalize what I was saying before about the envelope being regular from above. Envelope being regular from above means that the envelope is, as we say, weakly concave, okay? So minus the envelope, if you add a suitably large quadratic, it becomes convex. This means that you have a sort of relaxed subgradient inequality. So if this was not here, then this would be simply a convexity. Now we have this extra negative term. This is 1 over gamma weak convexity. And this actually holds for any subgradient in here. Now actually, I can also remove this hat. Limiting and regular subdifferential for this kind of functions are actually the same. But okay, here I reconnect to a point that was made before in the talk by Harold, that so the important thing to notice, so if you flip this inequality, so if you change the sign, what you obtain is a quadratic upper bound on the envelope. Okay, the envelope satisfies this quadratic upper bound for any v, not only in the subgradient, but actually in a convex hull. So I mean, we are getting a stronger sort of quadratic upper bound that involves many more subgradients. But why is this important? Because again, it was the same point was made in the earlier talk. If you think of gradient descent, the only thing that you need, I mean, usually think about Lipschitz differentiable functions, but the only thing that you need is a quadratic upper bound. You never use the quadratic lower bound. If you have a concave function, you can use any step size that you want for doing gradient descent, okay? And so this quadratic upper bound of the envelope gives me the, I mean, suffices to recover the same gradient descent type inequality that I had in the convex case. Again, I'm taking a long detour because we had arrived to this inequality before, even without involving this. But let's see what, but this interpretation actually gave us something more. Because what we have shown is that since, let me go back, this inequality holds for any subgradient in this, of this function, and the subgradient of this function involves the convex hull of this, this means that this type of inequality not only works for proximal points, but also for convexified proximal points, okay? Now, to some extent that I'm going to show next, so this envelope function can be used as a merit function, not only for the proximal point, but even for the convexified proximal point, which seems weird, but it is not actually. Because what you're actually showing here, this iteration that we are showing here, are maybe they're not proximal point iteration on phi, but in general, they're proximal point iteration on the so-called, on the proximal hull of phi. The proximal hull has this very weird definition, which, but to our purposes, what is the proximal hull? Is the largest weakly convex function, 1 over gamma weakly convex function that supports phi, okay? But here then the question is, okay, I have, let's trust that this is really proximal point algorithm on the proximal hull of phi, but then I would expect here, instead of the envelope of phi, to have the envelope of the proximal hull because of the discussion that we were doing before. But this is actually what we do have, because it is a known result that the prox of the proximal hull is equivalent to the convex hull of the prox, okay? And not only that, but also the envelope of the function is equal to the envelope of its proximal hull. Now, all this, if you're not familiar with this, may look very, confusing, but this is actually, it has a very standard parallel with convex optimization, because if you think of minus the envelope as a conjugacy operation, what you're writing here is that the proximal hull is the biconjugate. And what you're saying here is that the conjugate of phi is equal to the conjugate of the biconjugate, which is a standard result in convex analysis. And here you don't need phi to be convex, right? This holds for every phi. And this is actually not, it is not a chance, let's say. It's really a generalized conjugacy because, yeah. Anyway, you can really see all this envelope as, so in standard Fenchel convex conjugacy, you define the convex conjugate as a supremum, where you have a coupling function which is the inner product, right? You do supremum of xy minus phi of x, okay? Here, instead of considering this inner product xy, if you consider minus a square norm, what you obtain is exactly what is called a phi conjugate, okay? And for this kind of generalized conjugacy, all these identities are preserved. And there is much more to say here, which I will skip, because, for instance, you could be tempted to choose, instead of a gamma here, or you choose a lambda different than gamma, perhaps smaller. And in that case, you would obtain a so-called double envelope or less really envelope. And then you can talk about Klee envelopes if you take the approach from above, generalized to generalized distances, and so on. So, really, this simple expression here hides a lot that is very interesting. Now, okay, I will speed up a bit now. So, so far we have recovered the gradient descent interpretation of the that we had in the convex case. Now, what I'm interested in is checking how the envelope, how tightly it matches the function. So we know, it's very easy to show that minimizers and infimum of the envelope, even in absence of convexity, all agree with the function phi. What I'm interested in, and I will explain in a while why, is if the same can be said about local minimizers. And to understand that, we have to introduce some observations. So it all revolves around the properties of fixed points. So what do I mean, first of all, of a fixed point? Again, I say that x bar is a fixed point of prox if I have an inclusion. So instead of here having equal sign, I have an inclusion. So whenever x bar belongs to the prox of itself, of x bar. Now, whenever this happens, you can show that it is not only is it a fixed point for prox with this parameter gamma, but it's also a fixed point for all gammas strictly smaller than, for all gamma primes strictly smaller than gamma. Not only that, not only for if you reduce gamma, it will still be a fixed point, but it is what I call a regular fixed point, meaning that it will be a singleton. So it will be the only element in there, okay? So this gives the, exploiting this fact, we can define a sort of threshold, which is the highest gamma for which some point x bar is a fixed point, where we conventionally set it to 0 if it is not a fixed point for any gamma. And this threshold here says that for any gamma strictly smaller than that, my point will be a regular fixed point. And for every gamma strictly larger than that, it will not be a fixed point at all. Okay? And this is very important in answering our original question about what is the relation between local minimizers. And this is another observation, is that whenever you have a local minimizer, then this threshold is positive. What do I mean by that? This simply means that if x bar is a local minimizer, then for all gamma small enough, it will be a fixed point of the proximal map. And for all gamma strictly smaller than the threshold, the local minimality will be preserved by the envelope, and even strong. If the original was strong, also the new minimizer in the envelope will be strong. And for any gamma strictly larger, it will not be a minimizer. For gamma equal, we don't know, but strictly larger, we know it will not be. Strictly smaller, we know it will be. And here is a very easy example of a function which has only two feasible points, so 0 and 1. And if you do some math, you can see that the point 1 is fixed for every gamma smaller or equal than 1. Okay. Now, so this means that this gamma that I defined, so this capital gamma, this threshold will be 1. So it is the largest gamma for which this is a fixed point. And in the picture, you can see the envelope for gamma equal 1/2, which is strictly smaller. And you can see that indeed local minimality and even strong local minimality is preserved. But for gamma 1 and more, local minimality is not preserved. Okay. And why does this, all that I said so far, matters? So here, let's go to the practical considerations. So let's say that we want to accelerate this proximal point algorithm. We have seen in the convex case that we can use smooth minimization techniques. Now, general practice, okay, that again, here just for proximal point doesn't make sense. I mean, it makes sense for other splitting algorithms, but okay, play along for the moment. We can try to enhance speed by modifying the geometry. So instead of considering proximal point with respect to the standard Euclidean metric, you consider the metric induced by some positive definite matrix M, which can indeed yield improvement. The problem is that it changes the complexity of the algorithm. Because say that I'm able to compute the proximal mapping without this M, I have no guarantee that I will be able to compute the proximal mapping with some arbitrary M. Okay. So the question is, can we avoid doing this? And the answer is yes, and it relies on 3 properties of the envelope, just 3. So in general, the envelope is continuous. So it's not differentiable, maybe. In the convex case, it is, but in general, it is not. It's just continuous. We have this sufficient decrease. I mean, you remember the envelope can be used as a merit function. And let's say, in quotes, almost surely, any fixed point of the proximal map is regular. So if X is a fixed point, chances are that it is the unique element of the prox of itself, because there is only one gamma, so the threshold for which it can be multivalued. And as we argued before, this means that we preserve local minimality and even strong local minimality. So the key insight then, if you combine the first 2 properties, is that, so let's consider this point X bar. So I know that, so I fix X and I compute the proximal map X bar. I know this inequality is satisfied. But I also know that the envelope is continuous, which means that in a small region around X bar, the envelope will still be smaller. And how can I quantify this? For instance, I can reduce, instead of taking -1/2 gamma, I can slightly relax this inequality here by some C in 0, 1. And now I know that this inequality doesn't hold only for X bar, but it holds for any Y close to X bar. How close, I don't know, but okay, just enough to know that it exists. Okay. And now I'm not going into the details, but if you combine, let's say, actually, all the 3 actually, also 1, 2, and 3, not only 1 and 3, you can show that in a sense that I will make a bit more precise later. if you have a sequence that converges fast to some fixed point x star, then also the envelope will converge fast, whatever fast means. And if you think about it, this is totally not the case for the cost, because if your sequence y approaches x star from outside of the domain, the cost is always plus infinity. But the envelope will approach there instead fast in a way that I'm defining next. Okay, after explaining what the algorithm template is. So the algorithm, the template for just a continuity-based algorithm is the following. So the first step is to compute a standard proximal point, so that I call x bar, in the standard metric, so plain operation. Then let's say that I compute a fast direction at xk. What do I mean by fast direction? Say that you retrieve it by Newton type methods. After all, you're trying to find a fixed point of the prox, which means you're trying to solve a nonlinear equation. You can compute d using quasi-Newton methods on this nonlinear equation. And the important thing is that you don't need any notion of direction of descent. Okay, so d can be anything. And then you start with tau equal to 1. You do a almost standard backtracking with a slight difference here. So you start with tau equal to 1. And tau equal to 1, of course, you obtain only this second part, xk plus d, and you check, does this point satisfy this relaxed inequality? If it does, you accept it. If it doesn't, you reduce tau. Okay, and this is the standard backtracking technique. But the difference here being that in the standard backtracking technique, here I would have xk. So I have a direction at xk, and then I'm computing a direction xk plus d, and then I backtrack like this, right? I go back, I reduce the magnitude of this direction. Here instead, I have 2 points. I have xk here, the prox xk bar here. My direction will point here, and instead of going towards here, I approach this other guy. So I'm taking convex combinations between x bar and xk plus d, always approaching x bar. And I know that this line search will eventually always be accepted because it is simply the continuity of the envelope which guarantees that. This same thing can be generalized for any splitting, as I will maybe talk about later. And now, the question here is, does this work? So say that I have fast directions which are really fast, so that are so-called superlinearly convergent. Okay, so if I assume that I have these directions which converge faster than the iterates themselves, is my line search smart enough to understand that, oh, these directions are fast, I should accept step size equal to 1? Because if I accept step size equal to 1, then the iterates reduces to xk plus 1 equal to xk plus d, right? So that guy will not be there. Xk plus 1 will be xk plus d, and I will have superlinear convergence. And because of the tightness, so this the fact that the envelope goes fast whenever an iterate goes fast to x star, you can actually very easily show that at least when you converge to a strong local minimizer, actually you don't even need strong, you just need a quadratic error bound. In any case, unit step size will be accepted, and you're guaranteed that your algorithm will go fast. So to conclude, I mean, at least this half presentation about the Moreau envelope, I want to, let's say, advertise the envelope under 4 different aspects, all related to what I call tightness, in the sense that its ability to tightly capture all the relevant information of the original function. So first of all, it can be used as a merit function for proximal point iterations. And you remember we discussed lambda and 0,2, and you cannot do any better in general unless you put other assumptions on phi. For instance, even if you have a strongly convex function, you cannot go necessarily beyond 2. So take the indicator of 0, then the iterations will be something like this. And in order for them to converge and converge to 0, lambda has to be strictly between 0 and 2. Another point is that the envelope preserves strong local minimality or local minimality, but actually does it in a smarter way. Because if you remember this picture, for gamma large, this local minimizer will be totally unseen by the envelope, okay? So this means that it actually only captures the important local minimizers. So if you enlarge this gamma, this point will no more be a global minimizer, a local minimizer for the envelope, which means that any descent method on the envelope will skip that. Thirdly, okay, I haven't talked about this, but you can actually also show that, first of all, the envelope is always lower than the function, smaller than the function, so this gap, let's say, is always greater or equal than 0. And you have a nice thing that equality holds if and only if you are at a fixed point. And this may be of little interest, but now, if I remember correctly, I have to double check later. But for instance, in standard analysis of okay, now I'm jumping forward, but in a proximal gradient descent, when the non-smooth function is also non-convex, you know that you have convergence whenever gamma is strictly smaller than 1 over the Lipschitz constant of the smooth function. But instead, you can actually show that it also works for gamma equal to 1 over L if you consider this gap here, where the envelope function will not be the Moreau envelope, but will be the so-called forward-backward envelope, so the envelope associated to proximal gradient. Anyway, and the last thing, which was crucial in the working of that fast algorithm template, is the fact that the envelope is smart. It understands whenever a sequence converges fast to a strong local minimizer. And why I spent so much time on the Moreau envelope, because the point that I want to make is that all the envelopes that you can think of are connected to proximal methods, so Douglas-Shachford, proximal gradient, Davisy difference or convex and whatnot. They all satisfy these 4 properties that are key to provide fast algorithms based just on this splitting algorithms. So, okay, now I will go a bit faster, but I will make some, I will add some structure to the problem to make to give a meaning, let's say, to this, all this so far only theoretical inquiry. And let's make an example of the proximal gradient, and we will construct the envelope related to the proximal gradient. And if I have time, I don't know, but in the last part of the talk, I would like to show how you can generalize this to general splitting algorithms, more or less general splitting algorithms. And now, so we have, in this case, we consider a cost function, which is the sum of a function with Lipschitz gradient and a function g, which is prox-friendly. Now, this is more practically relevant because in some applications, you can really structure the problem as such. And to make it even more nice, I can also say that global Lipschitz gradient is more the time too much to ask. Local Lipschitz also works, but I mean, we need to discuss a bit more on that. So, I mean, I don't have time to, but trust me, I mean, mostly whatever I say also works relaxed in that condition. Now, the proximal gradient iteration does what the name proximal gradient say. So it does a gradient iteration and it composes with a proximal map, okay? And so it is standard knowledge that, I mean, if you expand the definition of the proximal map, you remember you had something like that appearing in the proximal map. And then you can see xk plus 1 as you can see this prox precisely as this parametric minimization here. Now, here, of course, this is a parametric minimization with respect to this variable x. So I can totally disregard these gray terms, so f of xk and xk, which are constant. But I include them because I want that this function of 2 variables that I call m of xk satisfies this so-called tangency condition. So if the 2 variables are the same, then I want to recover the original function. So if x is equal to xk, this goes away, and I have f of xk plus g of xk, which is my cost function. And so this idea, I mean, then in the same way that the Moreau envelope was the result of the value function associated to this parametric minimization, then we define a proximal gradient envelope, or I mean, for historical reason now, it's a forward-backward envelope. In any case, and which is simply the value function associated to this minimization problem. Now, let's see what properties it shares. So I will call T the Proxgrad operator. And as we saw in the previous slide, I can express this T as a parametric minimization of this model. And so my envelope function will be the minimum of this. And by definition of T gamma, this also will be equal to, if I replace W with any minimizers, which by definition are that. Now, okay, this is only true provided that I can guarantee that minimizers exist, but under the assumption that we have minimizers always exist. And here is the model as we had before. So the first observation is that, if you remember, if I computed this model in XX, I will give phi of x. So in particular, since the phi gamma is the global minimizer over W, in particular, it will be smaller than the value that it has for W equal to x. And so I obtain this inequality here. Then this function here, f, satisfies Lipschitz smoothness. I have a quadratic upper bound on that. So if I replace this by this, if I lower bound it as such, so a quadratic upper bound at W, so the gradient is at x, and what I obtain is an inequality of this form. So if I replace, for W equal to the x bar, in which case I obtain exactly x bar will be my forward-backward envelope, then I have this sort of sandwiching property. So phi at the Proxgrad point is smaller than the envelope, is sufficiently smaller than the envelope, okay? And I call it sandwiching because of the first one, this will be also greater or equal than phi gamma of x bar. And the important thing here to observe is that, similar to the case of the Moreau envelope, computing this forward-backward envelope only requires one call to the Proxgrad operator. So because I need to compute the function, I need to plug the value W in here. W equal to x bar being the result of a forward-backward step. Great. So, okay, let's put all these things together. Actually, let's also observe something more. I mean, if you do some easy algebraic manipulation, you can express this envelope in terms of the Moreau envelope of G, like that. And so f is continuous, the gradient is continuous, the argument here is continuous, the envelope we saw before is continuous, the Moreau envelope. So the result is a continuous function. And again, okay, you can do some, some nice things as we did before with the Moreau envelope, and you can obtain some convergence results for relaxed proximal gradient. But the important thing is that you can replicate verbatim all the arguments before and show that this function satisfies agreement of strong and for local minimizers. And this means that, up to introducing this threshold on the step size. And you can also interpret now a convexified proximal gradient as a scaled, this time, subgradient ascent on the negative envelope using the same arguments we did before. And when G is convex, then you can, of course, all this discussion is true whenever gamma is strictly smaller than 1 over L. But in any case, when G is also convex, then you can show that this function is, again, differentiable in the same way that the Moreau envelope was. And you obtain, again, a sort of gradient descent interpretation of the proximal gradient method. It is not needed for us, but I mean, it's a nice parallel with the Moreau envelope, and I don't know. Anyway, again, so the important part is not this subgradient interpretation, but the fact that I have both continuity and this sufficient decrease. And then I can do the same backtracking algorithm that I was that I outlined for the proximal gradient, for the proximal point. And yes, this has been indeed done. And Bella, for instance, is for the, it's a more general framework where instead of Euclidean distances, we have Bregman distances. And yeah, I mean, and especially this PANOC or ZRFPR, I mean, engineers, let's say, use them a lot in control problems because it is very fast, but it also only uses proxgrad iterations. So it really uses elementary operations, but thanks to all this continuity of the envelope, it is able to converge fast. Anyway, okay, let's see some more, what more we can do with envelopes, okay? And let me talk about a bit slightly more structured problem. And let me start with, okay, what we're going to do now is to introduce so-called block coordinate algorithms. So block coordinate means that instead of updating, so let's say that I have a problem in which my variable is structured in, let's say, in n components, in n blocks. And the idea of block coordinate updates is to update only the ith block. So to sample an index I and only to update that and to leave everything else unchanged. And the classical way of analyzing this kind of problems, and which is not what we're going to talk about, but I will use it for reference, is this one in which our function, we have a smooth function f, which is coupled and which satisfies a sort of blockwise Lipschitz gradient continuity, and a non-smooth function g, which is, however, separable. And this is super important, the separability of that function. And it's important for two reasons. First, to make these iterations meaningful, because then the ith block of this, it's really based only on the prox of the ith function and the ith gradient, I mean the ith block gradient of f. So you really save a lot of computation as opposed to doing a full update. But even more importantly is that all this, the analysis that, I mean, pretty much all of them, in order to establish convergent results for this kind of methods, use the cost, show that these iterations satisfy some descent on the cost, okay? And so our non-standard setting instead is flipping the two. So we want separable f and non-separable g, okay? And of course, the result will be, I mean, we will be able to do that thanks to the fact that you're using the envelope function. So the setting that we're doing now is what I just said, but there is a big problem now, even before talking about convergence analysis or whatnot, is that now the efficiency of block coordinate update relied on the fact that I could compute the ith block efficiently, okay? In this case, instead, if I have a non-separable block, so I cannot decouple this proximal mapping of this weird function g, then in order to compute the ith update, I first have to compute the full update and then only take the ith block and discard all the rest. So this seems nonsensical, okay? Because, okay, what's the point? I already have the full update. Why do I want to just proceed along the ith one? And so we have these two problems. First one, yeah, does it make sense? I mean, and the second one, we don't have any more descent on the cost, precisely because if we do block type updates, then we may even escape the domain of the function. And so in general, of course, to answer the first question, in general, it doesn't, but there are many special instances in which it does. And one of them, for instance, is finite sum. So in which I want to minimize sum of smooth functions plus non-smooth regularizer. And the way to do so, I mean, there is a smarter way to do it using this Campoi decomposition, which was presented by Harold earlier. But okay, I will go with the trivial consensus formulation. And it will actually be interesting to see what happens if you do this reasoning with the Campoi decomposition. But anyway, so if I add now a consensus constraint, then I force basically all the variables to be the same. But still, my function f will be separable, my function g will be non-separable. And for this special structure, it is very easy to see that because of the consensus constraint, every component of the prox will be the same. And it's very easy to see that actually they all amount to the prox of G, small g, the original G, evaluated in the average. So the idea is that I just need to update the average, okay? And indeed, if you do block coordinate type on this reformulation, what you obtain is an incremental gradient method, which was independently developed by, under the names of Finito or Miso. But thanks to this approach, we get a much higher degree of generality. And okay, I will skip the details. The fact that these algorithms are incremental means that I pay the price of doing block coordinate updates by I have to keep something in memory, okay? And every time I update the memory entry corresponding to the index I sampled, but other than that, every iteration amounts to just original small g prox and a gradient only of the ith function. Okay, I will go a bit faster now. So in general, so this was just an example, so these finite sum problems. So in general, where do these block coordinate updates make sense when G is non-separable? And the idea is that suppose that you know the prox at one point, which can be a sort of an inductive assumption. Then the working requirement is that computing the prox evaluated, okay, this should be boldface, sorry. Computing the prox, if I update the argument of the prox only along a direction, then this should also be easy. And examples include this consensus formulation that we saw before, or the sharing problems where instead of consensus you want to distribute resources, or L0 group sparsity, for instance, or simplicial constraints, because if you want to project on the simplex, unit simplex, it involves solving a small subproblem. But if you just move along one direction, then the problem becomes much simpler. And the gist, the way to explain convergence of all this kind of algorithm is just, okay, the envelope satisfies a super easy descent property, and everything follows, okay? All the convergence analysis follows, and it works for fully non-convex formulation. You can use whatever sort of sampling strategies you want. You can also account for individual step sizes to give different weights depending on the different Lipschitz modulus. And you can also avoid storing memory. You can use some limited memory variants. Do you have 5 minutes? Or okay, I will try to go super quickly then. Okay, now I would like to show how we can build the idea of how this envelope works, and I will consider the Douglas-Shackford splitting as a starting example. So we have seen that already in the past. So the iterations are like this, and in this case we are requiring both F and G to be prox friendly. Now, usually this prox, the first prox especially, is set valued, but under an additional assumption that the gradient of F is Lipschitz, then we have actually a characterization, so it becomes single valued. And for gamma small enough, we have the same characterization of the convex case. But now, knowing that this Sk is equal to this, we can plug it back inside there. So if you replace it here, then this one becomes, this Vk is actually a proximal gradient update at U. So Douglas-Shackford becomes really forward-backward composed with an extra prox to some extent, and some averaging happening there. So the rough intuition here, this also works for Daviesian splitting and others, okay? I'm just giving an example. So the rough intuition is, if this red prox was the identity, so let's cheat, if it was the identity, then what we would end up with is just a proximal gradient method. Instead, this prox is a mapping, but not any general mapping. It's something that satisfies some nice property, which is because you can show that it is both Lipschitz continuous and also strongly monotone because of the assumption of that. So this brings to the idea of considering a more general setting in which we have a so-called model similar to the proximal gradient, so a so-called majorization minimization model that satisfies these tangency conditions and this, let's say, sandwiching property. And G, we require it to be this mapping G, which was the prox in our previous case. We require it to be any strongly monotone and Lipschitz map. And this gives rise now to what I call it an algorithmic envelope. So, okay, this GPMM would be generalized proximal marginalization minimization. So this algorithm is identified by this mapping G, satisfying this strong convexity, strong monotonicity and Lipschitzianity, and this marginalization minimization model M. So that is the envelope, the algorithm, and this is the corresponding envelope. And so this generalizes many known envelopes. And the idea is that all these basic properties hold. Whatever G satisfying this strong monotonicity and Lipschitzianity assumption you make, not only prox, you can put whatever, and you have something like that. And okay, I'll jump quickly. Sorry, I went very fast here, but I mean, in any case, if you plug in some parameters and you have some, so if, for instance, if you consider the ratio between the strong monotonicity and the Lipschitzianity of this G and this M1 and M2 appearing there, then you can easily show that as long as you can make this guy greater than 0 for some lambdas, then you have guaranteed that you have convergence analysis. This is a super relaxed way. This is very loose, okay, because I'm not using any information on G other than it is strongly monotone and Lipschitz differentiable. But this, for instance, is enough. I mean, I just plug inside these values of M1, M2, MG, LG, and this is the, for instance, in the case of Douglas-Shackford with lambda equal to 1, this is the range of step sizes that I can cover. So the blue is the one that we established in 2020, which is tight and which was also rediscovered and actually tightened even by Alcantara and Takeda in the talk that was done before. This is the bound by Li and Pong, and this is instead the simple bound that you obtain by just plugging these things inside. So it's very suboptimal, but you just plug it in, and you don't need to think about anything. And okay, here I'm generalizing on the, I'm using like the x-axis corresponds to weak convexity versus, the ratio between weak convexity and Lipschitzianity. And yes, this is all. Sorry to take much time. So I hope that I convinced you that envelopes have many uses for in the both analysis, but also the enhancement of splitting algorithms. These are an FNT manuscript coming up soon. With soon have a very fluid meaning because we've been there on over 10 years, but now we really have something. And there is a lot more to say. I mean, there are many generalizations of all of this, and I will thank you with the last envelope of the talk. So thank you very much for your attention.
Is there any question?
Thank you for interesting talk. You mentioned Bregman distance, Bregman divergence, and the extension, and I know you propose some algorithm using the Bregman distance. So my question is, what is the challenging point extension to the?
Sorry, what is this?
What is the challenging point is in extension to the Bregman divergence on the study of the proximal point algorithm?
Thank you for the question. And yeah, so the most challenging point, as soon as your distance generating function has full domain and satisfies some, I don't know, strong monotonicity or whatever, everything follows pretty straightforwardly. But when the function has not full domain, so you have some boundary issues, so then there it becomes complicated. And you can still say something, you can show some decrease on the envelope and whatnot, but it's actually, when we deal with non-convex problems, it is very challenging. I'm not aware of any work which successfully addresses, even for plain proximal gradient, that the limit points of the sequence satisfy some necessary condition for optimality. Because if you also look at analysis in the convex case, just Bregman proximal gradient, the convergence analysis is based on the fact that the cost converges to the optimal cost, sort of. And then because of convexity, you can say something, if you add some assumption on the Bregman distance, then you can show that also the entire sequence converges there. But in the non-convex setting, I'm not aware of any result which even for proximal gradient method can successfully address that. I may be very wrong now, but actually, and I welcome if there are any comments in regard. I'm looking forward to that. But yeah, I would say that is the most challenging. Yeah.
I see, I see.
But thank you very much.
Thank you.
Any other question?
I want to ask about the lambda. That's it. So in the last slide, you show some restriction for lambda,
Yes.
for theoretical guarantee. But in practice, how can you find the appropriate lambda? Is it possible to do backtracking or something like this to find lambda for this case?
So usually the backtracking, I would do it on gamma. So gamma is not appearing here.
Yeah.
But okay, if I go to the
yeah, gamma you mentioned.
So for instance, okay, this is gamma here. So this will be my G. So G depends on this parameter gamma. Now lambda, usually you take it equal to 1. I mean, unless you want to do some averaging. I don't know. To be honest, I mean, the short answer is I don't know. The long answer is that usually it is this parameter gamma that plays, I believe, more. It has a higher role in determining the convergence speed of the algorithm. So I mentioned at the beginning that everything you can make it work in the local Lipschitz setting, and in that case, you would do a backtracking on gamma. Maybe you can integrate it with a backtracking on lambda. That is a good point, but I'm not sure.
I see. So Arya, when in the Arya slide, you said that lambda should be between 0 and 2.
Yes.
And the parameter setting, it satisfy between 0
yes,
and 2.
so for the case of the proximal point algorithm, so this one would be the identity, and this one would simply be the proximal mapping. So in that case, if I go to here, so in the proximal mapping, this is exactly 1 over gamma. 1 over gamma, you have identity here. So this row of the model would be 1, but also row of G would be 1 because this will simply be the identity.
Yeah.
And so in that case, I believe that if you plug it here, I mean, this goes away. This is 1. I mean, yeah, this is 2 over lambda minus 1. It reduces to, which is exactly 0.2. But in any case, this bound here is very, very loose. Okay, in general, this is just I'm just using this strong monotonicity, and this. If you do a much refined analysis, as you also did in your work, I mean, you get something much better. But,
I see. Nice.
Yeah.
And one more question. So I thought you mentioned Arya that gamma, if you set gamma to 1, the local solution is gone, and you show some curve.
Yes.
Graph or page around 6 or something. You show nice. So somewhere. So I was
local
wondering.
minimizer.
This one. So theoretically, always gamma equals 1 gives such a tendency.
So it all revolves around this definition of the threshold. So if you take the maximum gamma, the largest gamma for which you have a fixed point, then every value before that, every value strictly before that preserves local minimality. Every value strictly above that doesn't preserve local minimality. So in that case, that gamma happened to be 1 because the largest gamma for which that was a fixed point of the prox is 1.
I see.
After that, no minimality. Before that, minimality is preserved.
I see. The property was shown, utilized somewhere. I mean that the figure is very interesting and nice.
Yeah, I mean the way I use this is the fact that similar to if I think of this algorithmic acceleration, I mean, you know that an important condition is to convert, I mean, a sufficient condition is to converge to a strong local minimizer or something like that, right? So as long as my gamma is not that very bad gamma, then I can guarantee that if I had a strong local minimizer for the function, it is still for the envelope. And that is where
I see.
strong fast convergence
I see.
holds.
Okay, got it.
Yeah.
Oh, interesting. Yeah,
Thanks for the
nice.
question.
Thank you.
Thanks again to the speaker.
Thank you, Pierre, for the introduction. Well, first of all, let me thank the organizers and Liken for hosting this nice seminar, workshop. So this, my field actually, it's more econometrics and statistics. So it may be a little bit different from what you usually do. However, well, in research in econometrics or statistics, at some point, we need to implement the method. So at some point, we need to employ optimization methods. So that's why collaborating with optimization people is very interesting for me, because I can learn a lot of things. Well, so this work on factor models in high dimension is a joint one with Terada Sensei from Osaka University. Well, so first I will introduce the modeling that we consider when we think of factor models. So I will spend some time on this because you may not be familiar with factor models. Then I'll present the theoretical properties that we studied, and I'll illustrate these theoretical properties through some experiments. Well, so first of all, let me set the ideas, what I mean by high dimension, because it's factor models of high dimension. So, well, first of all, here we consider parametric models. So parametric models. And here, high dimensionality is about the large number of parameters that we aim to estimate. And typically, in multivariate modeling, so we observe a random vector, and we would like to specify some joint distribution, right, for the random phenomenon that we observe. And well, most of the time, when you want to specify a multivariate distribution, this so-called curse of dimensionality appears. So, for example, you can specify some copula for your vector of observations, and at some point, the number of parameters that is related to the joint distribution explodes with the dimension. So that's called the curse of dimensionality. Explode, so what I mean by that is the complexity order, so the number of parameters to estimate can be p squared, p power 3, 4, even more, actually. And well, to handle this problem, basically there are two main viewpoints, the dense one and the sparse one. So the dense one, so you probably are familiar with it, ridge method, Tikhonov method, regularization method, right? However, in this case, if you apply the ridge, for example, shrinkage, you will not, so you constrain your parameters, but you will not foster sparsity. Why? Because it's differentiable at the origin. However, if you want to foster sparsity, so that means you have zeros in your parameters, then you should apply non-differentiable penalization functions. So that's why I termed here regularization or penalization. We will shrink the parameters to 0. And so the main viewpoint here that I will employ in this talk is the sparse one. Okay, so we perform what's called variable selection. Now, let me introduce the factor model framework. So what we observe is a vector, p-dimensional one, xt. So xt can be IAD or time series. So here, in this talk, I consider time series data, so dependent data. And so the left-hand side of the equation is observable. This is what we observe, xt. And we assume the decomposition written on the right-hand side. So this lambda star times ft plus some epsilon t. So let me describe what is done here. ft is, so keep in mind the dimensions. P, okay, is the dimension of xt, can be very large. ft is a random variable called a factor variable. It's a vector too, so m dimensional. But m is much, much smaller than p. So the idea is that we summarize the information through a small number of variables called factors. As for epsilon t represents the error, basically. So it's also called idiosyncratic variable. So the dimension is p. So the right-hand side, we do not observe it. We don't observe the factors, and we don't observe also the error, right? So here, once again, on the factors, aim to summarize the information contained in xt. But this is summarized through a small number of variables, which are called factors. As for epsilon t, well, it captures the item specifics, or what's called also the local features. So for example, if you consider some data, so economic data, especially in financial data, we may consider that the equity returns, so stock data returns, they are driven by a few factors, which represent the market, plus some factors specific for a given company or sector. You may also think about the GDP or the inflation, which are driven by a few factors, so representing the business cycle, plus some measurement errors. Now, let me describe the types of factor models that we can consider, depending on the assumptions we make on the model. So let me just go back to here. I didn't mention lambda. So lambda is a very important fixed deterministic parameter. So it's something that we will need to estimate. Okay? So lambda is not random. It is a deterministic quantity. So the lambda star, the notation here, lambda star represents the true parameter. So, well, in factor models, we have the first separation between what's called exact factor models and approximate factor models. So here, this is about the assumption specified on the correlation for the idiosyncratic variable epsilon t. So if we assume that the covariance matrix of the idiosyncratic, the error variable epsilon t, is diagonal, then we are in the situation of exact factor models. But we can relax this assumption, assume some correlations in the error variable, and in that case, psi star is assumed, so in that case, psi star is non-diagonal, and we are in the context of approximate factor models. And also, we have the fixed factor model and dynamic factor model. So in the fixed factor model framework, ft has only a contemporaneous effect on xt. So this is what's written actually in this equation. But we may also actually specify some, we want to specify some effect from past factors. So in that case, ft may have an effect on xt through its lags too. So that means, in that case, if you go up here, you will add plus another lambda times ft minus 1, plus another lambda times ft minus 1. So in that case, we are in the context of dynamic factor models. So here in this talk, I will only focus on the exact and fixed factor model, because the main idea will be to estimate the lambda factor matrix. So this is also called the loading factor matrix. So here, lambda star, the parameter lambda star, to keep in mind the dimensions, it is a matrix of dimension p times m, called the loading matrix. And here, I will assume that m, the number of factors, is a known quantity. So again, if you can think of p very large, 500, 1000, but m is very small. M can be equal to 3, 4, 5. That's the idea of using factor models. You want to reduce the dimension. But there are many techniques that exist to estimate m using the data. Now we make some assumptions also on the random variables f and epsilon. So we assume f is centered with variance covariance matrix M, ff, denoted here. And we have some orthogonality between f and epsilon t, so they are not correlated. And finally, we assume that this psi star matrix, which is the covariance of the error variable, will be diagonal in this talk. So based on these moment assumptions, now if you take the variance covariance matrix of xt, denoted here by sigma star, you will obtain the decomposition written here. So we have lambda star MFF, lambda star transpose, plus the variance covariance matrix of the error variable epsilon t. So actually, this is related to the literature on high-dimensional estimation of variance covariance matrix, using here factor models. As for the vector of parameters, I will denote them by theta. So theta will contain the parameters in lambda, so using the vectorization operator. And theta psi will be the parameters in psi, so vec h operator. So you take the by symmetry, the diagonal terms in the lower triangular part. But actually, if psi is assumed to be diagonal, it will only be the diagonal element. Now, I will also denote the true parameter by theta star throughout this talk. Now, the question is how to estimate these parameters, lambda, psi. But also, I've mentioned before that ft is a latent variable. So this is something that we do not observe. So how do we estimate these quantities? Using the data. So first, let me talk about lambda star, the estimation of lambda star. So this is probably the most difficult problem in a factor model. The identification issue related to lambda. The main idea is that you can rotate lambda and obtain observationally equivalent models. So let me describe a little bit further this issue. So this is called the rotational indeterminacy issue, meaning that so the factors are only identified up to a rotation matrix. So that means you can rotate lambda star without changing the implied variance covariance matrix of your observations. Mathematically, it means that if you consider an inversible orthonormal matrix M, R, with dimension M times M, you have the equality written here in the middle. So the rotated one versus the non-rotated one, but you have an equality. So this implies that you do have observationally equivalent models. So there's a problem for the identification of lambda star, actually, to uniquely fix lambda. So to uniquely fix this quantity lambda star and MFF, what we need is that, so given this cross product, we need the restrictions to uniquely fix these parameters. So in total, actually, we need M square restrictions, because an inversible matrix M times M has M square free parameters. So in this literature on factor models, many restrictions were proposed in order to uniquely fix these parameters, lambda star and MFF. So in particular, if you look at this paper in Analytic Stat of Bai and Lee, in their table 1, they summarize actually a bunch of restrictions. So in particular here, I mentioned identification condition, IC, number 5. So they assume that this MFF matrix is the identity matrix, and they assume a special structure on lambda star. So the lower part of lambda star is a lower triangular matrix. By doing this, you can ensure that the model is, the factor model is identifiable. So identifiability is a key issue in factor models. Now, the estimation method. So basically, it can be split. See, the estimation method can be divided into two methods. The PCA approach, principal component analysis approach, and the likelihood approach. So if you consider the PCA approach, the problem can be specified as a least squares problem. So here, what we can do if we use the PCA method, we can estimate both f, so the latent variables, and lambda, using this least square type loss function. So here, the quantities that I need to estimate are f and lambda. The sample size here will be denoted by n, so small n. Okay? So that means there are already a lot of parameters to estimate. But we have a closed form solution for this. X, this is the matrix of the data that we observe, the data matrix. So there is actually a very big literature on PCA methods for factor models. Yeah, I should insist on this. If you use the PCA approach, you can only estimate the latent variables f and the lambda matrix. Okay, so this leaves out the estimation of psi, the variance covariance matrix of epsilon t. That's something you can do if you consider the likelihood approach. You can estimate lambda and psi. However, you cannot estimate at the same time the factor variables, ft, right? So this likelihood approach is based on the factor model decomposition of the variance covariance matrix. So to be precise, if you take a Gaussian QML criterion, so you will minimize this divergence, so the log determinant plus the trace. So the data contained in my sample variance covariance matrix, S hat. And we estimate the parameters lambda and psi. Okay. So here with this decomposition, that means I implicitly assume that my variance covariance matrix of my factors is the identity matrix. This is a commonly used assumption. However, here we can estimate both psi and lambda. So under the exact factor model, so psi diagonal under this assumption. So these are some results established in the literature for this estimator. So the properties that we consider here are the asymptotic properties. So when the sample size goes to infinity, we look at consistency and asymptotic normality of the estimator. But we have two frameworks. First one is when the dimension is fixed and n goes to the infinity. So we have already an old result. And Bailey extended these results when the dimension goes to the infinity. So in that case, it's much more complicated to handle the theory. As for, so here, as I mentioned, it's the psi diagonal. So actually, the diagonality assumption can be quite restrictive. We may want to allow some cross-correlation in my error variables. So this, the idea of relaxing this diagonality assumption is quite actually old in this paper of Chamberlain and Rothschild. So they relax this assumption and they assume that psi is, the spectral norm of psi is bounded. So the max eigenvalue in absolute value is bounded. So under this, this framework, if we assume that psi is not diagonal, then there is an identification problem actually, because we have more parameters. So that's why we need to consider the case that p goes to infinity. So if you consider the approximate factor model, so you relax the diagonality assumption, you can only consider the case, the high-dimensional case. So in this situation, a recent paper of Bai and Li established the asymptotic properties. Bai and Liao, in this 2016 paper, assumed sparsity on psi. So they assumed that psi is non-diagonal but sparse. So they established some consistency results. And in a 2020 paper with Terada Sensei, we studied the Gaussian maximum likelihood-based estimator of psi, so psi assumed to be sparse. We also consider another divergence, so the Frobenius norm, actually. So it's a least square type estimator. And we also established some theory for the estimator. So I hope it was clear, the two framework, PCA framework and likelihood framework. So here in this work with Terada Sensei, we consider the likelihood framework. However, from now on, I will essentially focus on the properties of this parameter lambda. So I've left something out of the discussion when I consider the likelihood framework. What about the estimation of the factors, the latent factors? Actually, we can do so. We can estimate the factors based on the estimation of the lambda parameter and the psi parameter. So the idea is that first you apply some algorithm to get a numerical solution for lambda and psi, and given these estimators, we can build some estimator of the latent variables ft. So using, for example, this type of estimator, generalized least squares. There are other types of estimator. However, you will always get in your formula the data. Okay? You can filter your latent variable ft. So the viewpoint from now on will be the following one. I will assume that psi star is diagonal. I agree that it's simplification. It simplifies the framework. So as a future work, we would like to relax also this diagonality assumption. We work with in a fixed factor model setting, so no past effect of ft. But we assume that lambda star is sparse. So it contains potentially a lot of zeros. So the point is to build some estimation framework for estimating a sparse lambda star and establish the theoretical results. I hope it's clear. So let me explain the motivation for specifying sparsity in lambda star. So lambda star is assumed to be sparse. So that means potentially it contains many zeros. So the sparsity in lambda star, it means that, so there are many zeros in lambda star. So that means that so the rows and or the columns of lambda star have many zero entries. So that means that if each variable in my vector of factors, fjt here, relates to only a small number of elements in xt. There are actually some economic applications of this concept of sparse factor lambda star, sparse factor loading. So for example, if we are in the presence of local factors, meaning that factors that affect only a subset of the observables. So you can think of some industry-specific shocks in a firm-level dataset. So here I will define the sparse support of my factor loading matrix lambda. I define it as this set of indices S for which my parameter lambda is not zero. My true parameter is not zero. So here, keep in mind that theta star lambda is the vec operator of the matrix lambda. So here, this represents the kth parameter, kth entry of the vector theta lambda. So here, the true parameter is assumed to be sparse. So that means S here will be much smaller, is the sparsity assumption. It will be much smaller than the total number of parameters in lambda. So lambda is a matrix of dimension p times m. So the total number of parameters is pm. So we assume that S, the cardinality, is much smaller than pm. This is the sparsity assumption. So actually, if we look at this paper of Bai and Lee, in their constraints for identification of the factor model, so in particular the constraints assumed on lambda, their conditions include some cases where lambda star is a sparse. However, it may not be the sparsest matrix. So our framework consists in considering sparse lambda star, but we do not assume any sparse structure a priori, actually. So our framework covers any arbitrary sparse structure for lambda star. And because of the rotational indeterminacy problem in factor models, so this rotation problem for the lambda matrix, so far, actually, no work has been done on the specification of a sparse framework for lambda star, except 2 papers. So the archive paper, so our working paper, and a paper done, a very recent paper done by Uematsu and Yamagata, where they work within the high-dimensional framework. So P potentially goes to infinity. And they specified a PCA-based framework for the estimation of a sparse lambda matrix. So in particular, they assumed what's called weak factor models. So this is about the eigenvalues of the common factor part, so lambda transpose. And your variance covariance matrix based on the factor model decomposition, you have this part plus the psi matrix. So the weak factor model is about the maximum eigenvalue of the common factor part. So the common factor part is lambda transpose. So they assume this actually the rate of divergence of the maximum eigenvalue. So their estimator is a PCA type estimator. So this is this least square type loss function, and because they aim to foster sparsity in lambda, so what they do is that they add this lasso type penalty function, right? So this L1 norm. So I think you are familiar with it, with their tuning parameter gamma n. So here the important point is here. So they assume that this one is not actually such a strong condition. However, for the identification of lambda, they assume that lambda transpose lambda is diagonal. And I will show you after that there are some cases in which this restriction is violated, actually. So their estimator is actually quite similar to a previous work done in, if I remember, JRSS B paper. So it's a PCA type estimator, actually, on this one. So they establish some consistency and support recovery properties. But again, because it's a PCA type problem, PCA type method, so the estimation of the psi matrix is left out of the problem. So what they do is that they estimate F, so the latent factor, and lambda, but they do not estimate psi. Now, let me discuss their constraints for identification of lambda. So lambda transpose lambda diagonal. Let's say that your true matrix, your true lambda matrix, satisfies what's called the perfect simple structure. So perfect simple structure corresponds to this type of structure. So as you can see, you have some clustering. But the clusters do not overlap with each other. So if you compute lambda transpose lambda, you will get a diagonal matrix with this structure. Yeah. But let's say that you have a structure like that. So it's a sparse matrix, as you can see. However, if you apply the cross product, you will not get a diagonal matrix. But if you apply the product lambda 2 transpose lambda 2, you will not get a diagonal matrix. So in that case, if you apply their algorithm, so their package is available on R. So here we have the heat map. On the left, we have the true loading matrix lambda, sparse one. And on the right, we have their estimated, so the estimated lambda matrix by their method. Well, as you can see, the estimator is quite far from the target. This is because of these, actually, the presence of these overlaps. So their constraints, lambda transpose lambda, is violated. And due to this violation, well, their estimator does not perform well. So that's why our now framework appears here to actually answer this problem of estimating any arbitrary lambda matrix, sparse lambda matrix. So here, as I mentioned, most of the existing works so treat lambda star as satisfying the constraints for identification. So that's because of this problem, actually, the sparsest true matrix is overlooked. So, so here are the conditions that we assume on the random variables f and epsilon. We assume that M is fixed, okay? And we work within the high-dimensional framework. So the high-dimensional framework here, what I mean by this is that P will be indexed by the sample size. So P will be denoted by Pn. Potentially, it can vary, so it will vary with N. Potentially, it will diverge with N. So the whole point will be to get some scaling condition between P, Pn, and N when we will establish the asymptotic properties. And yeah, so we will work actually under this parametric family. So that means, so the idea is that for a given n, we will have a parametric factor model, which is given in here. So we work under this probability measure, which is indexed by the parameter theta n, the factor model parameters. So this, so the total number of parameters that we estimate is actually Pn times m plus Pn. Why? So Pn times m represents the number of parameters in lambda. Because we assume that psi, so the psi matrix is diagonal, so we have the diagonal parameters. So that's why in total we have Pn times n plus Pn parameters to estimate. Again, it's the condition on psi diagonal, it's essentially to simplify, okay, the framework. The idea will be to extend this to relax the diagonality assumption in future work. Now, the criterion that we consider is this one. So it's a penalized criterion. So it's also called penalized M estimator. So for a given n, we have an estimator, theta hat n. When it exists, it belongs to this minimization problem. So ln theta is my loss function, and Pn is so the penalty function. Okay, so it can be. So actually, in our framework, we considered the SCAD and MCP. The reason is the lasso does not work well, actually. So for ln, the loss function, so it's a likelihood type loss function, but actually likelihood, well. So actually, I would be happy if you have any idea about this part. So here we consider two divergences. The squared Frobenius norm divergence. This one here, so it's a least square type loss function. And this one here is a Gaussian loss type function. We actually looked at other types of loss functions, so such as the von Neumann divergence, if I remember correctly. So it involves the matrix logarithm, but it's really difficult to handle this actually. So finding a nice loss function for estimating covariance matrices is quite difficult. So by nice, I mean a loss function which does not involve any square root of the matrix or any inverse of the matrix, or so that's actually quite difficult to find such a divergence. So we consider these two types of loss functions, and as for the penalty functions, we consider these two non-convex loss functions. So the SCAD and MCP. So actually, if you do employ some penalization methods, I would advise you to actually use non-convex methods. Because the lasso will generate actually a bias in your estimators. So, so maybe I will quickly go over these conditions. So these are what's called regularity conditions. So it's quite common actually in statistics or econometrics. For the data, we need also to assume some probabilistic conditions on F and epsilon. So on the top, actually, we consider time series data, so we assume some mixing conditions. So it's quite different from stationarity and ergodicity, actually. So assumption 5 will allow us to apply some exponential inequality, actually. Because if you work in a fixed dimension, to establish the asymptotic properties, it's quite straightforward to use a central limit theorem or law of large numbers, right? However, if all your dimensions, actually, if all your quantities are indexed by the, so they are indexed by the dimension, you cannot apply central limit theorem as is if the dimension diverges, because you have some triangular arrays, actually. So that's why the main tool that is employed, the main method that is employed when you consider high-dimensional problems, the main tool is concentration inequality to get some theory. Assumption 6 is about the sparsity. So sorry, I modified a little bit the notations now because everything is indexed by n. So I have indexed the sparse support by n, so Sn. But let me briefly discuss the implication of the sparse condition. First, so it's important to explicitly specify the norms we work with. Why? Because of the high dimensionality. If you consider equivalence, so norm equivalences, you have some constant that appears every time. And the constants, they depend on the dimension. So we need to be quite careful about this. So spectral norm, Frobenius norm. So Sn represents the total number of non-zero parameters. So if you look at the L1 norm of, so the L1 matrix norm of the true factor loading matrix, lambda, we have this order. So this actually will imply that potentially we have many zero entries in the columns of lambda star. And on the right-hand side, we have this lower bound on the true L1 norm. So this implies that actually we also have some restriction on the total number of non-zero elements in the columns of lambda star. Because L1 norm, so you take you will sum up the elements in the rows for a given column. So this actually bound is important to separate the effect from the common factor part, so lambda, lambda transpose, and the idiosyncratic part. So it's actually an important condition. So maybe this part I will skip it due to the time constraint. So let me go through the theory part. So the asymptotic, so here the consistency of the factor model-based variance covariance matrix. So here under the suitable regularity conditions, we can establish the consistency in the Frobenius sense of the variance covariance matrix, so sigma hat n. So we have this, so this part actually concerns the, so this first part here comes from the control of the expansion of the likelihood part. And here we have a biased part. So the biased part comes from the penalization of the parameters. So AN so is represents the derivative, my first derivative of my penalty function. So if you think of the lasso, actually the lasso penalization, an will be the tuning parameter simply. So the way to build the estimator of sigma hat n is actually a bit tricky. We need to make some matrix perturbation on lambda and psi. But for a given lambda and psi, here we get the consistency of the variance covariance matrix. So this result actually does not tell us anything about the consistency of lambda and the consistency of psi. Okay? Here we only get the consistency of the variance covariance matrix. Now, how to get the consistency of lambda and psi? Here we need to rely on some constraint for identification. So here, so the question is about the uniqueness of the factor decomposition. Because of the rotational indeterminacy, lambda is not uniquely fixed. So here what we do is that we rely on this condition of Anderson and Rubin. So actually the literature on factor model started a long time ago. So as you can see, 1956. So here we rely on this condition, so for which the upper square matrix of lambda star n is lower triangular. So the idea is that we have this structure in lambda. So with the upper part, lambda m, satisfies this condition. So the diagonal elements are assumed to be positive. So this condition, I will refer it to as the Anderson-Rubin's condition. So actually, also we have a sign indeterminacy. I did not mention it, but because of the cross product lambda transpose, we have a column actually indeterminacy and a sign indeterminacy. So actually, the positivity on the diagonal elements allows to avoid this sign indeterminacy. So we may think that this condition is not suitable for sparse estimation, but we can slightly relax it as follows. So actually, if there exists some permutation matrix Pn, such that the rotated loading matrix Pn times lambda n satisfies Anderson's and Rubin's condition, we can solve the rotational indeterminacy. So that's why we will work to get the consistency of lambda. We will work in this parameter space for lambda star n. So this space here contains the true parameter. So here, basically, you should see Pn as a way to reorder the rows actually in lambda n. So using this assumption 8, we can get the consistency of lambda n. We have obtained the consistency of the variance covariance matrix based on the factor decomposition. And using this Anderson and Rubin's condition, we can get the consistency of the loading factor, the factor loading matrix, and the variance covariance matrix of my idiosyncratic variable. So we get these true properties. They are known as the sparsistency property in the high-dimensional literature. So we get the consistency of my vector of parameters. So, but in this norm, for this norm, actually, so we lost a little bit something between the Frobenius norm and the infimum norm. So we have this convergence rate. So Pn is in the dimension of x, xt, and Sn is my this is my cardinality of my true support. So somehow it's a bit related to what's called oracle inequalities. And now the second property is called the sparsity property. So this property tells you that so when for a sufficiently large number of observations, we can correctly identify the true zero entries in lambda. So this is the meaning of this actually here equality with probability 1, with probability tending to 1. So we need some actually suitable conditions on my penalty functions. So they are actually given in here. And actually, we can also get the consistency of my estimator of my latent variables, ft. So using the consistency in here, we can get the consistency of my factor variables for any t. So ideally, we would like to get some uniform consistency, so uniform with respect to the time index. However, it will require actually another layer of complexity. So this is the main result, the persistency property. As for the, so in the remaining time, I think 10 minutes, right, if I'm correct. In the remaining time, I will discuss the implementation and show you some examples. So a simulation example. So here, actually, so we need, so here comes optimization. So how to solve the problem, actually. So we spend a real long time on devising some method to get suitable results. And one of the most complicated problem is the initialization of the problem. So the problem is highly non-convex. And if the initial point we start from is far from the true target, actually, it will converge to something which is really not good. So that's why we had to think of some trick to get a suitable initial value, initial point. So actually, we first get some initial factor model estimator, which is not sparse at all, actually. So actually, it's a strict factor model estimator, but because of this first stage estimator, so as you can see, we have some actually restrictions, but it may not give us an initial value which is sparse. So we need to actually consider this step Q, some rotation matrix, actually Q, which is orthonormal. So as you can see here, we need to solve this problem. We need to get some rotation matrix, which may be sparse. But under this actually orthogonality constraints. So we applied some algorithm from this optimization paper of Wen and Yin. And what we do then is that for a given gamma n, so gamma n is the tuning parameter. So we discussed a little bit how to choose this gamma n parameter. For a given gamma n, we apply these two steps until convergence, actually. So the optimization of lambda over there is done by some composite gradient descent type algorithm, for which we have explicit updates, actually. And then for a given lambda, we optimize the psi diagonal matrix. So using the AM algorithm. Calibration of gamma n. So gamma n, what we do is that we set the candidate values using this grid of values. So dim is the dimension of the problem. So it is done by actually cross-validation for the IID case. We need to be a little bit careful if we consider time series data, because we do not have the IID assumption anymore. So we need to apply what's called out-of-sample cross-validation. So I must mention that, of course, there are other methods to solve the problem. So we may apply, actually, a gradient descent for the joint vector, lambda m psi. So actually, I did try it, but I didn't get actually good, I did not get precise estimators compared to this two-stage method. So I tried actually gradient descent for both, but it did not work very well. And another way actually to solve the problem is by the EM algorithm. So another way to proceed. So you apply the EM algorithm for estimating lambda m psi jointly. I did try it, but I did not get very good solutions too in that case. Good solution, what I mean by good is MSE, so the precision of the SD solution, is not good actually compared to, well, this method. So far, this is the most suitable one. So I will be happy to discuss with you, optimization persons, if you can come up with something interesting. And also the EM algorithm for factor models is known to produce some unsuitable solutions, meaning that when psi is not diagonal, it does converge sometimes non-positive definite solutions. So it's also a problem. So in the last 5 minutes, I will show you a simulation experiment, show you how it works. Our method compared to the paper of Uematsu and Yamagata on the SOFAR method. So here we have what we do is that so here I skip the index n. So I just use p to simplify the notations. So for a given sample size n, given dimension p and given number of factors m, so we proceed as follows. So what we do is that we draw psi star as a diagonal matrix. So with diagonal elements simulated in this uniform distribution, and we draw a sparse true lambda matrix, lambda star, sorry, in this uniform distribution, the entries. So I will specify S, the number of non-zero parameters after. Then what we do is that we generate the data in this Gaussian distribution, so centered with variance covariance sigma star, so based on this decomposition. Then for a given sample xt, we solve our problem. So using the Gaussian loss function or the least square loss function, and MCP and SCAD penalty functions. And what we do then is that, so we have our estimator, our solution, and we need to compare this solution with the true lambda star. So that's why here what we look at is the percentage of zero coefficients correctly identified. We also need to look at the number of non-zero coefficients correctly identified. And we look at the MSE. So it's about the precision of the estimation. Then what we do is that we repeat the procedure 200 times. So we have 200 independent batches. An important point is that for each batch, new lambda star and psi star are drawn, are simulated. But the size of the sparse support of lambda star remains fixed for all the batches. So the total number of parameters in lambda star is p times m. So here I will just show you two structures in lambda. The first structure is the perfect simple structure with overlaps. So this type of structure, actually. So the overlaps corresponds to this type of overlaps. So here the dimensions are, I will show you the dimensions, p is equal to 120 and m, so we have 4 factors. And the sparsity is, here in this case, 165 non-zero parameters. So the number of zero parameters is 480 minus s. And we have here the arbitrary sparse structure. So typically something like this, totally arbitrary, the locations of the zero and non-zero parameters. And so here the logic is that 85% of lambda is sparse. So this is the sparsity degree. And we get, so for the perfect simple structure with overlaps, so here we have the column, our competitor, so far our estimator. And here we have for SGF and SLSF, SGF sparse Gaussian factor, so based on the Gaussian loss function. And on the left, you have the SCAD penalty function, and on the right, you have the MCP loss function. And on the rows, so we have P, the dimension, M, the number of factors, sample size. You have C1, C2, so the proportion of zeros correctly identified. The second row, the number of non-zero parameters, true non-zero parameters correctly identified, and the MSE. So the first comment here is that in terms of precision, the Gaussian estimator works better than the least square estimator. If you compare this SCAD Gaussian estimator compared to the least square estimator, it works better. But our method, in any case, SGF or SLSF works much better than the SOFAR estimator. We have much more precise estimations. It makes sense because actually it is known that the likelihood-based method provides more precise estimators than the PCA-based estimator for factor models. And so we have also the same observation for the arbitrary sparse structure. So in terms of identification, correct recovery of the zeros, we have better performances than so far, especially when the sample is a bit larger. So these figures are larger than the so far, but also better recovery of the true non-zero parameters, which is also an important measure. And finally, here we also consider the case of misspecification. So that means the true psi star here is simulated as a non-diagonal matrix, but sparse. However, we estimate our model under the diagonal assumption. So we have some misspecification. But still, in this case, we have some robust results for the estimation of lambda star. So the results are still actually quite good. So because of the time I need to finish, I will conclude. So the paper is has been updated recently. So it's an archive, and the code for application is on GitHub. As for future works, as I mentioned, we would like to consider to relax the diagonality assumption on psi. However, the difficulty in this case is how to specify sparsity if you have a sparse psi and a sparse lambda. So to identify where the sparsity comes from, lambda or psi is quite a difficult issue. Something that we work on now with Terada Sensei is this framework, so the matrix decomposition factor analysis. This is actually related to the Wasserstein distance. So actually this loss has links with this distance. So we concurrently look at the estimation of this model. And we also are interested in knowing if there exists some alternative matrix divergence for the estimation of variance covariance matrices, other than the Gaussian or the least square loss function. All right, and I finished. Thank you.
Thank you very much for the talk. I have to say that I'm a bit meaning very ignorant about the global setting, but when I saw at some point you mentioned this MCP and the SCAD function, which are sort of relaxations of, if I remember correctly, zero norm or something like that, or I don't remember what they relax exactly, but I was wondering why in the corresponding optimization methods, instead of using those SCAD or MCP, you could use also directly the, I think it's the zero norm or something like that. I don't remember exactly, but I encountered it in the past. And
so I think you think about the L0 norm, right?
Yes.
Okay, yeah, I think it's also a possibility. We may consider this. So you may reformulate the problem a little bit differently. So you may consider an estimator, which so the problem is here. So actually, you may forget this part, minimize this one under the L0 actually constraint. That's also another possibility.
But that
would... But I mean, here we took, so first we did not consider the lasso, so the L1 norm, as I mentioned, because due to the bias, and theoretically the lasso does not allow you to recover the zeros, so the sparsity property that I've mentioned. So the lasso does not work, actually. So theoretically and empirically, actually, it's not a very good solution to consider if you want to do sparsity. So that's why it's actually better to use non-convex method. So non-convex penalty function is what I mean. So this one, this loss function is a non-convex one. So the SCAD and MCP, as described in here. So the difference with the lasso is that for small, so the SCAD and MCP behaves the same as the lasso when you have small parameters. But for larger parameters.
Sorry, with lasso, you mean with L1 norm
regularization?
Yeah, the L1. Yeah. So I was mention instead, what about L0 norms? So which is even more or even some LP norms with P equal 1/2 or something
Yeah,
like that.
so L0 norm is also a possibility that that can be considered. We did not consider it, but it's actually something we will probably include in the future work I've mentioned on a factor matrix decomposition analysis.
Just to mention something, I don't know how related that is, but there were some research also about, I mean, some in between, I don't know, 0 and L0 and L1 norms, and L1/2 or something like that seems to be a good, but I don't know how related it is. And
L1/2, so you mean some
with P equal 1/2, so it's a
bridge.
it's
I think
a
it's some bridge. It's called bridge. I think this.
Yeah, I'm not really experienced.
But I think what you mentioned is I mean it's the separation between non-convex and convex penalization.
Yes, I mean yeah.
I think it's yeah. For
But
the
also in terms also of identifying sparsity patterns or something like that, this LP with P strictly between 0 and 1. I mean, I've read, I never done it myself. I mean, I trust these references, but then again, I don't know if it is related to your kind of problem. But
I think it's about the separation of convex and non-convex regularizations. So theoretically, but also empirically, it's better to use the case P smaller than 1. I think that you have in mind. So bridge actually can be included in our framework, but we would get in the theory part. Here, it's all about these parts actually. So if you use the bridge, you will have an explicit, a more explicit form of this first order derivative that will appear. And so these conditions are about so the penalty function, but also the choice of the tuning parameter gamma n. So it will be modified in this part, I think, if you use a bridge penalization.
Okay, I see. Thank you very much.
Okay, so since we passed time, so we can continue offline, I think. So thanks again for the speaker for the
Thank
talk.
you.
So my work is on functional analysis methods in machine learning. So basically kind of methods involving Hilbert and Banach space methodologies for machine learning. So the title of the talk is a bit long. It's an optimal transport and information geometric framework for positive operators and infinite dimensional Gaussian measures and Gaussian processes. So this is kind of the live work I have been working on in the last, like since coming to RICAN about 6 years ago. And so it's kind of like, it's kind of a geometric, basically geometric methods for positive operator, positive definite operators and Gaussian measures on Hilbert space and Gaussian processes, because these objects are all kind of intertwined with each other. And so, of course, geometric methods is actually kind of very general. So I'll be focusing on kind of the methods that derive from optimal transport and information geometry. Information geometry, which is a very big field in Japan. So this is kind of, so of course, this is kind of very, very big. The direction is very big. So I'm going to be actually very focused. So I will be talking about the generalization of the following geometric structures for probability density functions on Rn. So optimal transport distances and Fisher-Rao metric and distance and divergences to infinite dimensional probability measures on Hilbert space. And with concrete results on Gaussian measures on Hilbert space and Gaussian processes. And in general, we would like to study kind of the geometric structures of stochastic processes, but these results would apply to the covariance operators of the general stochastic process, kind of the second order structures of stochastic processes. So I have a lot of results, such as I would not be able to talk about everything. So I would probably focus on the optimal transport and the kind of the Fisher-Rao. I will probably mention the divergences in a little bit in the end. The divergence is actually quite general. So, because I have a lot of slides, but I will not cover everything, so don't worry. I will not talk about like 130 slides. So, so the functional analysis. So basically, mostly I focus on the infinite dimensional setting. So it does involve. So when we want to generalize all these kind of geometrical structures, all these distance and divergences for probability density functions on a Euclidean space to the infinite dimensional setting, it does involve a lot of mathematical techniques. So it involves the interplay of the following mathematical fields: operator theory, especially the theory of positive definite operators. This is the generalization of the theory of positive definite matrices to the infinite dimensional Hilbert space operator. So it involves many kind of quantity, many kind of generalization of many quantities that are not necessary for the infinite dimensional setting. And then it involves the Riemannian geometry also in the infinite dimensional setting, and Gaussian measures and Gaussian processes. And since these objects are infinite dimensional objects, when we want to do when we want to do something concrete, a concrete computation, we have to do finite dimensional estimation. And this is where we have to do kind of like a finite dimensional approximation. This is where the methodology of RKHS, reproducing Hilbert space, comes in the setting of Gaussian processes. And for obtaining sample complexity, we employ the probability theory on binary Hilbert spaces. So it does involve quite a few mathematical fields, but I will be very concrete. I will just the results I want to present are very concrete, and they will just focus on the basic Gaussian measures on Hilbert spaces and the corresponding Gaussian processes. So the motivation in the finite dimensional for the study of the geometrical structures in the finite dimensional setting, Gaussian measures on Euclidean space and symmetric positive definitions, they play a central role in statistics, probability theory, and machine learning. There are numerous practical applications. So there are applications in brain imaging, in computer vision, in radar signal processing, in brain-computer interfaces, BCI. So there's a huge literature on these objects in the finite dimensional setting and their applications. So why would we want to carry about the infinite dimensional setting? So one of the motivation or the setting for the infinite dimensional setting is a setting of Gaussian processes. So suppose we have like a nice compact metric space, for example, these interval from 0 to 1. So let's consider the interval from 0 to 1, for example. So the Gaussian process, it is is a collection of random variables indexed by t, and so that even for every finite set of points in T, we have a vector which is distributed according to a Gaussian measure. And this is fully determined by the mean and covariance functions, which are defined by these formulas here. And so, so since it's fully determined by the mean and covariance functions, we can often denote it by like just the mean and covariance function to Gp and K. And so this has been studied for a long time and we have a very well-established literature on Gaussian processes, and we have a kind of a correspondence between Gaussian processes and Gaussian measures as follows. So suppose, so this was like from 1972, so more than like 50 years ago. So we will focus on Gaussian processes with paths lying in, we just square integrable, so like functions in like L2T, so square integrable. So this happens if and only if the mean function is square integrable, and then the covariance function satisfies this property is called like the trace property of the covariance function. And so here we have this, and we have a one-to-one correspondence between Gaussian processes with mean function m, covariance function k, and Gaussian measures on the Hilbert space h equal to m2t nu. So with where m is just the covariance function here, and ck is a covariance operator given by this integral operator, where k here is a covariance function. So it's like the it's integral operator with the kernel function k. So this object is very well known in machine learning, and it has been studied extensively, and we will actually use it later on. So we can consider like, so this is an example of Gaussian processes. For example, this is on the left we have the Gaussian processes generated by the so for simplicity, which is considered the case when we have like the mean function equal to 0. So on the left we have the Gaussian process with the kernel function given by this Laplacian kernel, when a is equal to 1, and then on the right we have the Gaussian kernel, sigma equal to 0.1, and the Gaussian processes that with the Gaussian kernel is very smooth, so the paths generated will be very smooth. So we were talking about the interval t from 0 to 1 here. So this the H sample part basically is like a part from we just square integrable in the interval L2 like 0, 1, and so we can consider this as we have like a Gaussian measure on the Hilbert space H equal to L2 0, 1, and then we sample from this Sparse sample from this Gaussian measures on this Hilbert space. So it's an infinite dimensional Gaussian measure, and we sample from this Sparse sample from this Gaussian measure. So this kind of so in statistics in the field of functional data analysis, there's a lot of work in studying kind of this the distances and divergence between the Gaussian measures corresponding to Gaussian processes. So we have a very large literature in statistics. So basically, if we have the mean equal to 0, if we assume that the mean equal to 0, then basically we just study the distance or divergences between the covariance functions or the covariance operators. So there's a lot of work using the Hilbert-Schmidt distance. So this is not really optimal because it doesn't really capture like the kind of the positivity symmetry of the covariance operators. There's work utilizing the Wasserstein distance, and then there's also work in machine learning using the K-on divergence, and recently there's work in functional Bayesian neural networks using the Wasserstein distance. So one simple setting from machine learning is kind of the functional Bayesian neural networks, where they study like the compact labular divergence. We have the optimized some quantity that involves the K-on divergence between the posterior and the prior. So now for Gaussian measures, for example, this quantity here, we will talk about a little bit later on. The K-on divergence between P and Q is equal to infinity if P and Q are mutually singular. And it's difficult to sample the complexity when P and Q are, even when we have the exact formula, it's difficult to obtain sample complexity. And recently there's also work that replaced the K-on divergence by the Wasserstein distance. We will not, which is well defined, but actually it's not differential. But we actually talk a little bit about this later on. This is the one example for the motivation of the studying of the distance or divergence between Gaussian measures corresponding to Gaussian processes. So this is one example. So now, we would like to move from the finite dimensional to the infinite dimensional settings. And what do we mean by the infinite dimensional settings in this case? So if you consider the set of all probability measures on a metric space for the setting of the set of all probability measures on Rn, which is a non-parametric setting, this is an infinite dimensional manifold. But what I'm going to talk about is, it's different. I'm talking about the probability measures defined on an infinite dimensional Banach space. In particular, I'm talking about the Gaussian measures on a Hilbert space, infinite dimensional. So this is a parametric setting, but it's an infinite dimensional parametric setting. So I'm talking about this second part. This is what I'm going to talk about, and not the first part. So in the first part, often we have like this metric space is equal to Rn. So the kind of the underlying space is finite dimensional. I'm talking about the case where the underlying space is infinite dimensional, which in particular a Hilbert space. So how do we, so what are the challenges of working in the infinite dimensional setting? We have no natural reference measure because the Lebesgue measure doesn't exist on an infinite dimensional Hilbert space. So we don't have a natural concept of probability density functions. So for example, on Rn, we have this Gaussian density functions here determined by its, via the zero mean, for example, and it's completely determined by this covariance function. But it's not well defined. This density function is not well defined in the infinite dimensional setting. Because the sigma inverse is unbounded, and so this determinant here is not well defined. And this one, we cannot let it go to infinity, for example. So it's not well defined on an infinite dimensional Hilbert space. But nevertheless, we can, if we assume that we have probability measures on so let's see how we can define how a Gaussian measure is defined on a Hilbert space. So we have a probability measure on H, and then with finite first moment, we can determine we can define the mean. The mean is given by this formula here. So there exists like a unique M, so that M is given by this formula, and so it's going to mean, and if it has if the measure has finite second order finite second moment. If we have a finite second moment that exists a unique bounded linear operator C on H, so that we have this formula is given, so that it satisfies this formula here. And this C is called the covariance operator of mu. And so on Hilbert space, we have C is a symmetric, it's a self-adjoint and positive Chase class operator. And so this has been established a long time ago, and so we can define there's so given M in H and a self-adjoint Chase class operator, there's a unique probability measure so that its characteristic function is given by this formula. And we can show that there's a unique probability measure that satisfies this property. So this one is called the Gaussian measure with mean M and covariance operator C on H. So it's defined via this characteristic function. And very concretely, if we have like if this operator C here, it has infinitely many eigenvalues and corresponding to a normal orthonormal eigenvectors EK, and we can have a natural isolation between H and L2, the space square integrable functions, and then we can define the following probability measures on I infinity with one-dimensional Gaussian measure. So just we define this product here, and then this mu here is the Gaussian measures with mean function M and covariance operators C. Okay. So this is actually how we can define concretely on L2. If we kind of make that the natural isolation between H and L2, then we can define as an infinite product of one-dimensional Gaussian measures. So just very briefly, we're talking about a lot about Hilbert-Smith operators and trace class operators. So we just very briefly talk about review briefly Hilbert space. Okay, so this is like the Hilbert-Smith in the product between two operators. So it's given by this formula here, and in particular for self-adjoint Hilbert-Smith operators, we have the Hilbert-Smith norm squared, just a summation of all the eigenvalues squared. So just a generalization of the Frobenius norm in finite dimensional settings. So in general, it's with the trace of A self-adjoint times B. And okay. And for the trace class operator, the trace class norm is just given by the sum of, for self-adjoint operator, just a summation of all the eigenvalue, absolute value, and with the trace with the summation of all the eigenvalues. So of course we have so it's also called the nuclear norm on the more general like finite space setting. So when we go from the finite to the infinite dimensional setting, we have to be very careful because the identity operator is neither Hilbert-Smith nor trace class, because we have all the eigenvalues equal to 1. So the Hilbert-Smith norm and the trace class norm is always equal to infinity. Now on RD, we have the standard Gaussian measures N0 ID. There's no standard Gaussian measures on H because this measure doesn't exist. And so no isotropic Gaussian distribution on infinite dimensions. So we have to be very careful if we want to. We have analysis using N0 ID, and then we let D goes to infinity because it may or may not make sense. And it's often necessary to work directly with probability measures on H. So this one, we have to be pretty careful when we let D goes to infinity. So the correspondence between Gaussian measures and positive trace class operators, the geometry of Gaussian measures. So suppose we have mean equal to 0, then the geometry of Gaussian measures just corresponds to the geometry of the set of self-adjoint trace class operators. Okay, so now we were talking about like the generalization of the distances and divergence. So some of the distance and divergence are straightforward to generalize. So the Hilbert-Smith distance and the Wasserstein distance are straightforward to generalize, but the Fisher route and the distance or the Kullback-Leibler and Bernoulli divergence are not straightforward to generalize because they are generally not valid in the full infinite dimensional setting. So we have to be very careful. Okay, so first I will talk about the optimal transport is in particular the Wasserstein, the L2 Wasserstein distance. Suppose we have a nice, let's first consider the case when X is equal to Rn, and then we consider the cos function equal to the square cos function. So in the optimal transport problem between two probability measures nu0 and nu1 in Px, we solve this optimization problem. Here we minimize kind of the expected of the cos function C over the set of all choice measures of nu0 and nu1. And so this on the setup like well, all probability measures with finite order moment about P, then this if we take the P root of this quantity, then we get something called the P Wasserstein distance, and it defines a metric on this PPX. So it has been studied for long. Ultimate transport is a very big field in mathematics. It has been studied for a long time for Torres and Monge in 1781, so like more than 200 years ago to already study this. So in this case, he was actually studying kind of like the an optimal map P that maps between the two probability measures. So this one, if it exists, it's called the optimal transport map. it doesn't always exist. So for example, this is actually kind of a motivation. We're kind of trying to transport like from this pink here to this purple distributions here, like how to move sand and earth from one location to another with minimal cost. But this thing doesn't know, may or may not exist. For example, if we have like this kind of mu is equal to the direct delta measure, then if mu is not a direct measure, then the transport cannot exist. So the counterific formulation that we was at the beginning, this counterific formulation here still makes sense. So it's kind of a more general formulation. And so there are reasons that that says where this optimal transport map D exists. For example, if the two measures are all like kind of second, we have like finite second moment, and we have the square cos function, and the measures of the mu is actually very nice. And then we have that's a unique optimal transport map, and it has the form T is equal to gradient U for convex function U. For example, however, this results hold in the case when we have mu and nu are probability measures over RD, so it's not applicable in our setting. Now, in the Gaussian setting, the finite dimensional Gaussian setting, we have a closed form formula with a square cos function. So suppose we have two Gaussian measures on Rn, and then this was worked out like many years ago, so in the kind of early 1980s. So we have a closed form given by this formula here. And in the case when the mean is the same, then we obtain this one will be equal to 0, and we obtain something we call the Buritz-Wasserstein distance that Benjamin was also talking about before. So in the case when we have Gaussian necessities, in the case when one of the covariance matrices are, sorry, these are covariance matrices about operators. The covariance matrices are singular, non-singular, then we have the closed form formula for the transport map. So it's given by this formula here. So of course, in this case, we have the covariance matrices have to be non-singular because otherwise the inverse would not exist. Now, in the infinite dimensional setting, we have the same formula for the distance. So it was also worked out like in the early 1990s, and we have the same expression as in the finite dimensional case. It has been recently applied in the context of Gaussian processes. And we also like, so we have the same mean, then we have the Buritz-Wasserstein distance between the covariance operators. Now we have to, it is valid for singular covariance operators. So this is actually a very special property of the kind of optimal transport distance of Wasserstein distance, because later on, as we will see, this is valid. It has the same expression as in the finite dimensional setting. It is valid for all pairs of Gaussian measures. This is not the case with the Kullback-Leibler divergence or the Rényi divergences or the Fischer-Rao distance, because they are only well-defined for equivalent Gaussian measures. So this is a special advantage of optimal transport distance. It's always well-defined. However, it's not differentiable if I will talk about it later on, and then the transport map is unbounded, because if we look at this, back at this formula here for the transport map here, this has to be invertible, and in the infinite dimensional case, this operator would not be invertible. So the transport map is actually unbounded. So even though we have a very nice distance, the transport map is actually unbounded. So life is never perfect. Okay. So that is the exact optimal transport distance, the exact Wasserstein distance between two Gaussian measures on a Euclidean space. Now let's talk about the entropic regularization of optimal transport. So the exact distance is generally computationally demanding and can have very bad sample complexity. For example, it can have like worst case. It can have like worst case. It can be in the worst case, it can be exponentially bad. So that's a formulation called the entropic regularization. So instead of just minimizing the expected cost over the joint measure gamma, we add like a term. This one is called the one of the K divergence between gamma and the product measure of mu and nu. So this one is called the entropic regularization term, and so it can lead to it leads to more numerically something called the synchronic algorithm, which is more numerically efficient. So I would actually not talk about the numerical aspects of this method here, but I should talk about the in the Gaussian setting how well actually it improves the theoretical properties of the distance. So now when we add this term here, the OT epsilon between mu and mu is not equal to 0, so it's kind of biased. So what we can do is we can like do something called debiasing. So we subtract a half of OT epsilon mu and OT epsilon nu. So if we do this, then we have a proper divergence. It's called a Singhorn divergence. And it has been applied and studied a lot in machine learning. So let's see how it what the formula looks like in the finite dimensional Gaussian setting. So for two Gaussian measures, so this was worked out like a couple of years ago, and it's done via it uses the classical property of the maximum entropy property of Gaussian density. So we have, if X has mean 0 and covariance matrix C, then the differential entropy, so the differential entropy is given by this formula here, is maximum if and only if X is Gaussian. And so this quantity here, this is really kind of the mutual information. It's given by the, it's expressed via the differential entropy. And so if this quantity here is maximum, if only if gamma is Gaussian, then this is minimum if only if gamma has Gaussian. So the minimizer of this thing has to be Gaussian. The minimizer gamma here has to be Gaussian based on this maximum entropy property of Gaussian densities. And so this is how we actually solve for this problem. So the minimizer has to be gamma has to be a joint Gaussian density of mu0 and mu1, and we can express it has to have this form where so C0 and C1 are the original equivalent covariance matrices, and the C here is a cross covariance matrix, and we can express the K-on term in term by a very close form formula here. So we can plug this in, and we can solve for this optimization problem. So here's the closed form formula. So I'm just showing this formula to show that we have closed form formulas, and the unique minimizer gamma has to be a Gaussian measure. So this was done a few years ago. So let's see if we can generalize it to the infinite dimensional. It can be generalized to the infinite dimensional setting, but we have to be very careful here, because number one, the entropy is this entropy does not generalize to the infinite dimensional. So we have this formula, but it does not generalize to the infinite dimensional setting because we have infinitely many, the C has infinitely many eigenvalues, but the eigenvalues all go to 0. So it's actually not, this determinant is not well defined. And so we have like for two Gaussian measures, like, we have the joint Gaussian measure gamma, it has this form here. And so before we have this expression for the K-on between gamma and mu0 times mu1 is given by this formula. Now, because the right-hand side is no longer well-defined because these determinants are not well-defined, but the left-hand side is always well-defined. It can be finite if gamma is absolutely continuous with respect to mu0 times mu1, otherwise it's infinite. So the left-hand side is well-defined, but the right-hand side is kind of not well-defined. So the mutual information is well-defined, but the entropy is not. So here we have to consider like a very interesting property of infinite dimensional Gaussian measures. So like on RE, to have two Gaussian densities, always have the full support of all the whole space. If H is infinite dimensional, then two Gaussian measures are either equivalent or mutually singular. Either they have the same support or they have disjoint support. This is actually kind of a sharp break from the finite dimensional setting because of the Feldman-Hartrich theorem. And we have necessary and sufficient conditions for the equivalence of two Gaussian measures. And this was like worked out also like many years ago. So if we have two Gaussian measures mu and nu, then they are equivalent, so they have the same support, if and only if the difference of that means has to lie in the range of q to the half, or the same as range of q r to the half. And the covariance operator has to be related in this form here, by where S here is S here is the self-adjoint Hilbert-Smith operator. So they have to be related to each other in this form. So for example, if we shift the mean just a little bit, then they wouldn't have like disjoint support. And if gamma is a joint Gaussian measure of mu0 times mu1, then gamma is equivalent to mu0 times mu1 if its covariance operator satisfies this property here. So they are rated by the by this formula where gamma 0 is equal to kind of the diagonal of C0 T1, and we have this kind of cross covariance operator V here. So now V now here is a unique Hilbert-Smith operator with operator norm less than 1. And then we can compute this K-on divergence now between gamma and mu0 times mu, the mutual information. So it's infinity if gamma is singular with respect to mu0 times mu1, and otherwise if it's equivalent, then we have a closed form formula. And here now this determinant here is an infinite dimensional determinant. It's something called the Fredholm determinant. So it's given by this formula. So we have an infinite many eigenvalues under K, for example, then is anything the determinant of I plus a which is the product of the infinite product of 1 plus lambda k. So if we just have RA, then it's not well defined, but if we have like I plus A, then this product will converge. So the correct generalization of the maximum entropy property is not in the infinite dimensional setting is the minimum mutual information. So it's the mutual information that is well defined across dimensions. And so it's the minimum mutual information. And so if we have gamma and gamma zero, so gamma is a joint measure, a joint Gaussian measure of mu x and mu y, then it's kind of this mutual information is minimum if and only if gamma is a joint Gaussian measure. And in that case, it has a closed form formula. And then we can use this to analyze to obtain the solution to our problem. So again, we plug this in, and the minimizer now has to be a joint Gaussian measure. It has to be equivalent to mu0 times mu1, and it has to be a joint Gaussian measure. So if we kind of plug everything in, then we have this expression here. We have this kind of this optimization problem here. So we optimize over V, where V is a Hilbert-Schmidt operator and with operator num less than 1. So it's an infinite dimensional optimization problem that it can be solved, and it has a closed form formula. So it's actually strictly convex, and we can define, for example, we can define this function here. We can define this one in terms of V. Then we can actually compute this. We can compute this Fisher derivative, and then we can set it to be equal to 0, and we can actually solve for this. It's a little bit complicated technically, but we can actually solve for this, and it has a closed form formula. So there's a unique minimizer, and then we often like a unique form of the unique minimizing Gaussian measure gamma. Okay, so in the case of Gaussian measures with square cos function, we have closed form formula. Okay, and then we can also obtain the solution via something called the Schrodinger system, so that we can actually solve for this. Okay, when I actually skip this slide, because not so. And so using this, we can obtain the closed form formula for the synchron divergence. So this is the closed form formula for the synchron divergence. You don't have to worry about the exact expression for it. But when epsilon goes to 0, we obtain the square versus time distance. So when epsilon goes to infinity, which is this whole expression here will go to 0, and we just obtain the difference between the mean square. So everything here is well defined. Remember that we have this Fredholm determinant here of the form I plus the Church class operator. So these are all kind of finite dimension, all get finite. Okay. Okay. So what are the difference between the kind of the entropic regularization, the synchron divergence, and the exact versus time distance? So the exact versus time distance given by this formula is only defined on the set of self-adjoint. Like Chess class operator C0, C1 have to be Chess class, where the synchron divergence is actually defined over a larger set. It's actually defined the set of self-adjoint, but only Hilbert-Schmidt operators. So it's defined on a larger set of operators. So they are both well defined. They're always finite. So we saw just now that the compact level divergence, the Kant divergence, only finite from the Gaussian measures are equivalent. This is the versus time distance and the synchron divergence are always finite for any pair of Gaussian measures. So very nice property of optimal transport. But the regularized divergence has many nice theoretical properties. For example, it's differentiable, whereas the versus time distance is not differentiable in infinite dimension. Again, I wouldn't actually. So here. So this is the on finite dimensional setting for this for the square versus time distance. We can compute the Fisher derivative. So because we have the square root here, so it involves like a kind of negative square root here. So this expression is not, because we have this is the compact operator, so then it wouldn't be unbounded. So this whole thing is actually unbounded. Whereas we don't have that problem with the synchron divergence because we have the regularization. So we always so we can have like we have also like a closed form for the Fisher derivative, but it's always bounded. Okay, so everything here is bounded because we have the kind of the regularization. So when epsilon goes to 0, of course we will obtain the other. When epsilon goes to 0, we will obtain the other divergence and it will explode. But as long as epsilon is greater than 0, then everything is nice. So we can do for example, we can do gradient descent using the synchron divergence on the Hilbert space, but not for the exact versus time distance. So that was differentiability. Now, in the case of for the So that was differentiability, and now we talk about convergence. So we have a sequence. We have this results also known a long time ago. So we have a sequence of Gaussian measures. They converge in the exact Wasserstein distance if and only if the corresponding covariance operator converges in the Chase class norm. This is the Banach space norm of Chase class summation of all the eigenvalues, absolute value of the eigenvalues. So it's like an L1 norm. Whereas for the synchron divergence, we have the convergence if the covariance operators converges in the Hilbert-Schmidt norm, which is an L2 norm. Now, and this one is actually kind of nicer because we can apply loss of large number of Hilbert space value random variables to obtain sample complexity. It's more difficult with the Banach space norm. We do have loss of large number for Banach space value random variables, but for the L1 norm, it's actually more difficult. I will actually illustrate it very shortly. Okay. So now, kind of the formulas we had before. The formulas we had before are infinite dimensional formulas, so they are abstract formulas, and it's quite difficult to compute them directly. So what we can do is we can what we can do in practice, we can obtain finite dimensional approximation, and the Gaussian process setting is one such setting where we can have like finite dimensional approximations. Suppose we have the two Gaussian processes with covariance functions K1, K2, and then we sample like m point from the interval t from 0 to 1, for example. And so if we do that, then we have like two finite dimensional vectors distributed according to the Gaussian measures with covariance matrix KIX, where this one is the kind of the Gram matrix associated with the kernel K, and then so we can estimate the infinite dimensional formula in L2. So that because we want to study the distance or divergence between these two L2 Gaussian measures by the finite dimensional formula in RM. Now, so RM is not. So this one is actually a finite dimensional version of this. Now this one, RM is not a subspace of L2. So what we can do is we can carry out the analysis entirely using reproducing kernel Hilbert space operators. Okay. So basically, okay, I wouldn't go very fast on this, but what we do need for the sample, this is where the kind of the reproducing kernel Hilbert space or RKHS methodology comes in, is for the sample complexity. So we can define this operator kind of mapping from L2 to HK, given by this formula here, and then we can study like, so this covariance operator for the Gaussian measure CK is going to go to the RK star times RK. So we're mapping from L2 to L2, and then we have another operator mapping from HK to HK. This one is called RK, is called to RK times RK star. So we have these two operators which are very similar to each other, but they map between two different spaces. And then we can also have the covariance operator of RKI times RK star J, so mapping from HKJ to HKI. So these operators are actually used a lot in machine learning. They are not interchangeable. What we can do is actually I will actually skip this because what we can do is actually we can represent everything. We can represent all the kind of the divergences before using these RKHS operators. So this is like the infinite dimensional version. So expressed in terms of the RKHS operators in between the kind of the theoretical RKHS operators, and for the empirical version, we express in terms of the empirical version of these operators. Oh, sorry, I'm kind of going very fast here. So if we kind of do this representation, we have this representation in using RKHS operators, so we can apply laws of large numbers, and we can obtain this. This is the kind of the finite dimensional estimation of the synchron divergence for Gaussian processes. So here we have two Gaussian processes. This is the infinite dimensional version, and this is the finite dimensional version. Oh, sorry, I'm assuming I'm missing bracket here. And this is like their concentration in inequality. So kappa here is the size of the kernel, kind of the maximum of the kernel. It can be weaker, actually. This is kind of like a stronger, the assumption can be weaker. And so this is a dimension independent sample complexity because it depends only on the size of the kernel and the number of the sample size m. And so for Gaussian kernel, for Laplacian kernel, this kappa 1, kappa 2 is equal to 1. So we have this epsilon here, where epsilon here is the kind of the entropy regularization parameter. So it's dimension independent. Whereas for the Wasserstein distance, because we have the Chase class convergence, we actually do not have we do not have dimension, at least I don't have dimension independent sample complexity. It depends on the, for this, we actually need to, for the moment, we need to assume at least that one of the RQHS is finite dimensional. So this term here, we need to assume, otherwise it would be vacuous. So this is the difference between the kind of the entropic regularization and the exact Wasserstein distance. In the exact Wasserstein distance, we have the Banach-Chase class norm convergence, which is an L1 norm, and for the synchron divergence, we have the Hilbert-Schmidt norm convergence, and so we have nicer convergence behavior for the entropic version for the synchron divergence compared to the Wasserstein distance. So number one, the differentiability, the synchron divergence is differentiable, the Wasserstein distance is not differentiable. Number two, for the convergence, we have a dimension independent sample complexity for the synchron, and we don't have this dimension independent sample complexity for the Wasserstein distance. And we can also estimate, we can carry out the analysis using finite samples, because before we assume that the covariance matrix are known, but we can also estimate them from finite samples. Well, the analysis is basically the same. So this is an example here. So we have like these two Gaussian processes. We want to estimate them. So interval from 0 to 1, for example. And so this is like the interval t from 0 to 1 to the power d, where d equal to 1 and d equal to 5 and d equal to 50. So this is like the Wasserstein distance. And here we have the synchron divergence with epsilon equal to 0.5, synchron divergence with epsilon equal to 0.1 and 0.5, and this is the Hilbert-Schmidt distance. So we can see that for the synchron divergence and then the Hilbert-Schmidt distance, the kind of the convergence is very stable across different dimensions. But whereas for the Wasserstein, it's become a lot slower when d becomes large. So here we have m ranging from 10 to 1,000. Okay, so as I was differentiability, we were talking about budget before, and then so it has like much nicer behavior when we want to compute the barycenter, because it's always has a unique solution. Okay, so that was the optimal transport distance. So basically the message that when we do the entropic, so we have closed, okay, so there are several messages here. Number one, we always have closed form formulas between any pair of Gaussian measures. This is in contrast to the Kuhnbeck-Leibler divergences, with the Fisher-Rao distance later on, which are only well-defined, or which are only finite when we have equivalent Gaussian measures. Number two, when we do the entropic regularization, we have differentiability always. Number three, when for convergence and sample complexity, when we do the entropic regularization, we have dimension independent sample complexity, so it's a much nicer behavior. And then with the differentiability, for example, we have a much more well-behaved barycenter problem. Okay, so that's like, so by doing entropic regularization, we have many nice properties. That is the kind of the message. Okay, so that is the first part. Okay, so I think I already covered like 40 minutes, so I have like 20 minutes left. Okay, okay. So that would be I would not have time to cover everything. We'll talk about the Fisher-Rao metric and distance. So this is kind of more recent. And so for this, we have to focus on equivalent Gaussian measures, because this is not defined on all pairs of Gaussian measures. So the Fisher-Rao metric is a very kind of like a central quantity in information geometry. So suppose we have like a set of okay. So let's focus on the set of Gaussian densities here on Rn. So there's a one-to-one correspondence between the set and the set of SPD matrices of size n by n. And so it's given by, of course, the covariance matrices. And since because of the symmetry of the covariance matrices, we have like basically they can be like a manifold considered as a smooth manifold dimension n times n plus 1 over 2. And we can define something called the Fisher information matrix. So this is a very kind of classical quantity. So it's given by this formula here, and it defines if it's kind of positive definite. And in this case, it is positive definite, and we have something called the Fisher-Rao metric, or the Fisher information metric. It defines a Riemannian metric on this set, turning it into a Riemannian manifold. And we have a closed form formula. We have a closed, so it was also worked out a very long time ago. We have of course in the Gaussian setting, what is nice, which we can obtain nice and closed form formula. And since we have the one-to-one correspondence between the set of Gaussian densities and the set of SPD matrices, we have it corresponds to something called the affine invariant Riemannian metric on the set of SPD matrices, and it's given by this formula. So the metric is also very has a closed form formula. And of course, now this one, because when we are going to the infinite dimension, just like these formulas are no longer well-defined because the sigma here is, these are all unbounded. So this is no longer well-defined, the infinite dimension setting in general. They are only well-defined in very particular setting, and I'm going to show when they are well-defined. So for this, like we have, it's a Hadamard manifold. We have a closed form formulas. So Chris was talking about like this, for example, such a very well. It has a unique geodesic joining, and the matrices A and B has a closed form formula. We have a nice closed form formula for the Riemannian distance, and so it has a lot of very nice properties. So now I would like to generalize it to the infinite dimensional setting of Gaussian densities, from Gaussian densities on Rn to Gaussian measures on Hilbert space. Okay. So the challenge is now this formula is no longer, it doesn't generalize directly. When I talk about very briefly, and we talked about before, we have no natural reference measures and no Lebesgue measures, so we don't have like the concept of natural concept density functions. And so the Fisher-Riemann metric does not generalize directly. So what we want to do is actually, so the resolution for this, this doesn't generalize. The resolution is to consider something called the extended Hilbert-Schmidt operators norm and inner product. So this was done actually a while ago. Okay, so now we have done this before. Okay, okay, so we have this infinite, but we have this. Suppose we have a covariance operator, for example, which is a strictly positive Hilbert-Schmidt operator. So it has like infinite many eigenvalues, lambda k is always greater than 0, but then they always go to 0. So then since the eigenvalues are always going to 0, this will go to like the log, for example, go to negative infinity. So this log A will be unbounded, and log A inverse will be unbounded. This means they are always unbounded. So this expression is generally unbounded, so it's not well defined. It's only bounded in some very special settings. And so the resolution is to do something called the unitization in mathematics, or we call it regularization in applied math in inverse problems or in machine learning. But in pure math, we call it unitization. So they add like, instead of just constant A, we add like a gamma I, where I is the identity operator for gamma greater than 0. So if we do that, then of course the inverse is always bounded, and the log is also bounded. Now, however, this quantity, if we compute the log here for the kind of the Hilbert-Schmidt norm of this quantity here, for example, it's only finite if gamma is equal to mu, otherwise it's equal to infinity. It's because once again the identity operator is not Hilbert-Schmidt. So what we do is we enlarge the space of Hilbert-Schmidt operators, so it contains the identity operators called the extended Hilbert-Schmidt operators. So we consider a set of operators that form A plus gamma I, where A is Hilbert-Schmidt and gamma and I is an identity operator. So it's called the extended Hilbert-Schmidt or unitized Hilbert-Schmidt operators. And we can define something called the extended Hilbert-Schmidt inner product and extended Hilbert-Schmidt norm. So it's defined in this form. So that we have the extended norm of the identity operator is equal to 1 instead of equal to infinity. And if we do that, then we can consider the set of all kind of positive definite unitized Hilbert-Schmidt operators. So now this one is now a Hilbert manifold is the infinite dimensional manifold, and now everything is well defined. We can define the affine Riemannian metric on this manifold, and it has, because everything now is well defined because we have the extended Hilbert-Schmidt norm. Everything here is bounded, and then so it's also like a Hadamard manifold. So except now it's an infinite dimensional manifold, and we have a closed form formula for joining any pairs of operators. We have the closed form formula for the exponential map, the logarithm map, and the Riemannian distance. So everything is actually very nice and well defined. So this was actually done a long time ago. It was done by Lado Tongda in 2007, so like almost like 20 years ago. So now we actually use this for defining the Riemann, the Fisher metric. So again, so like we have no natural reference measure. So what we can do is we have like a partial resolution. So we consider a set of all probability measures equivalent to a fixed measure mu0. So if we do that, then we can consider the random Nicodim density here, the mu with respect to mu0. So this is always positive, and so we can now consider the generalization of the Fisher metric. So in information geometry, there's a lot of work in the infinite dimensional setting. We have like a kind of the Banach manifold of all probability measures equivalent to a given one, and so on. So this work kind of like this works are kind of very general and abstract. I'm just going to focus on kind of the set of equivalent Gaussian measures on Hilbert space. So not the full set, but the set of all equivalent Gaussian measures on Hilbert space. Remember, the Gaussian separators have to be related in this form. So we can consider the set of all Gaussian measures. We consider this. So we can fix the Gaussian measure mu0 with Gaussian supporter C0, and then we can consider this set here, the set of all self-adjoint Hilbert operators so that I minus s is greater than 0, and then so the set of Gaussian measures equivalent to mu0 is given by this is a set of Gaussian measure with covariance supporter C, so the C is rated to C0 by this formula. So this is parameterized by the infinite dimensional Hilbert manifold S, and so this one now is a Hilbert manifold. So so this set of all Gaussian measures equivalent to mu0 is a Hilbert manifold parameterized by this set. Okay. I will skip some slide. So now this is the formula. This is the definition of the Fisher metric. So we have this manifold S here, and then so before we take the log of the density function, and then we compute the derivative, and then we compute the integral. So here this is generalization. We compute the Fisher derivative. So we can compute the density, the Radon density of mu with respect to mu0, and then we can compute the log like before. But now we compute the Fisher derivative at the point S in the direction of V1 and V2, when V1 and V2 are the tangents in the tangent space. In this case, they are in the self-adjoint Hilbert-Schmidt operators. And so in this particular setting, so if this formula is only well-defined if these quantities are well-defined and they are in L2, in the space of L2 H with respect to mu. Now, in this case, we do have closed form formula, and we can actually compute. So it's actually, I'm going to go over this. So it's defined over something called the white noise mapping associated with the Gaussian measures mu0. I'm going to actually skip this, but it's defined using the white noise mapping. And we have closed form formula. So we have closed form formula for the radon nicotine densities with respect to mu0. So the formula is given by here just to show that we have a closed form formula. And we can take the log, and then we can take the Fisher derivative and so on. Okay. So in one particular setting where this S here is S and V are both just class operator, then we can express everything in a closed form formula. Otherwise, we can take the limit. Okay, I'm going to skip the next couple of slides. So finally, we obtain this is the expression for the Fisher metric. It's given by this formula here. And if we consider the correspondence between the Gaussian measures and the trace class and the covariance operators, then we have the corresponding Riemannian metric on the set of corresponding covariance operators. And so it's given by this formula here. So it's the same expression as in the finite dimensional case, except we have the Hilbert-Schmidt in the product here, and it has the same expression as before, except now that everything here. Now, in general, it's not. In general, this operator, if we consider it alone, then it's unbounded. But in this particular set, everything is bounded. So only on the set of Gaussian measures which are equivalent to each other. And we can do everything. We can generalize everything from the finite dimensional setting. We have a Hadamard manifold. We can compute the Levi-Civita connection. We can compute the Riemannian curvature tensor, the sectional curvature, etc. And we can compute we have a closed form formula for the exponential map, for the logarithm map. So everything is the same. So if we restrict ourselves to the set of equivalent Gaussian measures, then we have the same expressions as in the finite dimensional setting. So this is the expression for the geodesic, and this is the expression for the Riemannian distance. So it has the same expression as in the finite dimensional setting. And how is it related to the kind of the regularized the positive definite Hilbert-Schmidt operators before? So on the right-hand side, we have the exact Fisher-Rao distance, and on the left-hand side, we have this kind of regularized distance using the extended Hilbert-Schmidt norm and the unitized or regularized Hilbert-Schmidt operators. So on this side, on the right side is only well-defined for any pair of, for a pair of equivalent Gaussian measures. On the left side, we have this expression is well-defined for any pair of Gaussian measures. So we can use this left-hand side to estimate the right-hand side. And the left-hand side can be, for the left-hand side, we can also obtain sample complexity. So to summarize, So this is the story of the Fisher-Rao distance between Gaussian densities on Rn. We have the exact Fisher-Rao distance, we have the closed form formula, everything is nice and finite. Now on a Hilbert, infinite dimensional Hilbert space, between two equivalent Gaussian measures, we have the closed form formula, except we have the Hilbert norm is finite. Now, if we do not have equivalent Gaussian measures, then we can have something called the regularized Fisher-Rao distance. So instead of just A and B, we add like a regularized barometer gamma here, and using the extended Hilbert norm. So this one is finite for any pair of Gaussian measures. So we have two key components. We use the regularization A plus gamma I, and we use the extended Hilbert in the product and norm. And then when mu1 and mu2 are equivalent, then we can recover the exact distance by letting the regularization parameter goes to 0. And for the finite dimensional setting, we have the now we have a closed form formula for two equivalent Gaussian measures, but it's not straightforward to obtain finite dimensional approximation. Whereas for the regularized Fisher-Rao distance, we can have finite dimensional approximation, and we have like this very similar analysis as in the case of the optimal transport with the entropic regularization. So we can have this. We can estimate that we can represent everything in the RKHS using the RKHS operators as before, and we can obtain the very similar behavior. So this is like the infinite dimensional formulas, kind of the infinite dimensional distance and the finite dimensional distance, and we can also have the kind of the sample complexity. So depending on the regularization parameter gamma and the size of the curve and the sample size. So again, it's dimension independent. Now this gamma, so it depends on the gamma. So 1 over gamma. So it's very similar before with the synchron divergence with 1 over epsilon. So where gamma goes to 0, this will explode. Okay, so this gamma has to be greater than 0. So when gamma goes to 0, it will become vacuous. And so once again, so we can do for the Gaussian process setting, we can also do the very concrete estimation of the distance between the Gaussian measures. So this is the kind of two Gaussian measures corresponding to these two Gaussian processes, and this is and so here we set gamma equal to 0, 10 to the negative 6, and m come from 10 to like 1,000, and so this kind of the basically like it converges to kind of the distance of around 2,500, whatever, and then and these two Gaussian processes are much closer, and so the distance will be a lot smaller as we expect. So it converges something a lot smaller. Okay, now I would actually not have time to talk about the divergences, which actually, so it's kind of in the setting of divergence, actually pretty similar. We don't have, so we have like, for example, something called the alpha log that divergence, and then the alpha beta divergence. So we have the log and the determinant. These are between Gaussian densities on defined. These are defined for positive definite matrices on Rn by R on like sim plus and n. And so the determinant are not, in general, is not modified on the infinite dimensional setting, also the log. So these formulas are generally not, in general, they are not generalizable to the infinite dimensional setting. They are only generalizable to some particular setting. For example, we have like B inverse here, it's not unbounded. So everything will, like, in general, will be unbounded in the infinite dimensional setting. So we can do this something very similar. We can do something very similar. We can do regularization. We can do something we call, like we have the same challenges as in for the other settings. So we can do something called like the extension of the chess class operator. So it's actually, we can do the same thing. So we add like a regularization method gamma I, and then we do the extension of the trace. So we can call something called extended trace class operators. And then we can define something actually very, very similar. We can define something called like this one, something called the alpha log that divergence between trace class operators. So we can define everything, and then we can extend also. In this case, we actually need to extend the Fredholm determinant. There's something called the extended Fredholm determinant. And then we can also recover like and for example, in the case of the K-Young divergence, we also obtain if we let in the case when alpha equal to 1, we have the K-Young divergence, and we can let gamma go to 0, then we also obtain the exact K-Young divergence. So it's like we have like a very similar story using kind of we have to extend like the chess class operators and the set of chess class operators, and we have to extend the concept of the determinant. Anyway, I will not go over this, but it's actually very general. And we can also, this is one, for example, the kind of the calculation of the regularized Kayan divergence and Roni divergence is between these two Gaussian processes. So we have like very similar kind of convergence behavior. Okay. So this one actually has been applied for in a recent work, and actually it's for the applied actually for the set of the functional the setting about functional Bayesian neural networks I was talking about at the beginning. And so this gamma here, they choose a very small gamma. They choose it by fine tuning. There should be like I think that there should be like a kind of a theoretical way to choose it, but at the moment it's actually empirically chosen. Okay, so I have I have a lot of results. So to summarize, we're talking about the optimal transports and the kind of the Fisher-Rao and so on. So there's actually, so in the last couple of weeks, basically I have kind of constructed like a mathematical framework for connecting the purely geometrical theory of positive operators with the probabilistic and statistical theory of Gaussian measures and Gaussian processes. And so, for example, we have the generalization of the Fisher-Rao metric and distances between Gaussian measures from Rn to the Hilbert settings of Hilbert setting, like equivalent Gaussian measures. And then for this Fisher-Rao distance and also divergence, we need to do regularization, which is theoretically necessary. It's not an empirical method. It's actually a theoretical method. And this regularization leads to various very nice properties. And for the Wasserstein distance, we do not need regularization entropic for a well-defined distance. But nevertheless, when we do the entropic regularization, which is actually originally motivated by computational efficiency, we can show that by this entropic regularization leads to very nice theoretical properties like differentiability, convergence, and so on. So a lot of theoretical results can be obtained. Actually, I have done a lot of work, so you can actually check out my work. And of course, we would like to kind of extend it to the kind of so one of my aims is actually to extend it to the quantum setting. And also, it kind of would be very interesting to do something called the Hellinger-Kantorowicz distance that connects this to setting of information geometry and optimal transport. So, okay, so thank you very much. That's a lot of materials. Thank you very much for listening. I'm happy to take questions, comments, suggestions, and criticisms.
Sorry, I could not fully understand.
I'm sorry,
very difficult.
But,
entropic regularization. Yeah, you mentioned the benefit in the list. But is it related to A plus lambda I? So in a lot of numerical experiments, you mentioned that A plus lambda I is the regularization.
So that's a different setting. So actually, we have like two different settings. So this the second setting of A plus gamma I is actually for the kind of information geometric kind of quantities, and whereas this entropic regularization was the optimal transport. So they are slightly different, but the theme is kind of regularization. The same. Okay. But they are two different settings. So the first one is actually the first half is like optimal transport, and the second half is actually entropic, like the information geometry.
I see. Yeah, I was wondering how they're connected to each other.
They should be connected somehow, I think. But at the moment, I don't have like the good kind of unifying actually information.
Okay, got it. Thank you.
Thank you very much.
Okay, if not, so we would like to thank the speaker again.
Thank you for your introduction. Thank you for the organizations. My name is Tamle. I would like to talk about the optimal transport on tree system and application. So this work is more about the machine learning rather than the optimization field. But at the core of the talks, the optimal transport problem is just simply a linear programming with a linear objective and linear constraint. So it's quite simple for the optimization field. So let me start about the motivations why the optimal transport in machine learning. So the probability measure can be used for representation for various kind of object of interest. For example, we can use for documents in natural language processing, we can represent it as a distribution over the words inside the documents, or an image as the distribution over the pixel colors, or in a neural network as the distributions over the network operators, or in dynamical system, or here in topological data analysis. Here is just a lifetime to summarize the lifetime of the topological feature, the birth and the death of the topological feature, just 2D point clouds. Or in material science, we can represent a molecules at the distributions over the atomic position. Or even data sets in machine learning, we can consider as distributions over data points, its samples in the data set. For example, ImageNet as a distribution of image. And optimal transport is a natural geometry for probability measure. So Minh has introduced about the optimal transport. It can trace back to monks in the 18th century, and it also obtained several remarkable achievements. For example, the Nobel Prize in 1975 in economics for Kantorek and Kaufman, and a few medals in 2010 and later 2018 for Villani and Figali, respectively, and very recent for Caffarelli, the Apple Prize in optimal transport. It also appears in economics, applied math, and full math as well. So it's still an ongoing field. So here are some applications of the optimal transport in machine learning. So we can use the optimal transport to flow one data set into the other data set. So we can use that for domain adaptation when we just have a few samples for training, and we would like to have more samples when the data is scarce. Or we can use that as for neural architecture search in deep learning. So for a given task, we would like to search for a good architecture for that task. For even in causal estimation, we can use the optimal transport to estimate the counterfactual distribution, the natural width when one distribution, we observe one distribution and without any treatment, and we observe the other corresponding distribution at the other times. Or for object interpolation in computer graphics, here we interpolate from the sphere into a chair. Or we can use for generative model to generative the images, or we can use the optimal transport for LLM retraining. So since for LLM is trained on the public and large-scale noisy dataset, we can use the optimal transport to pruning, to select good data points and prune the bad data points for the optimal transport. So sorry for the training data. So let me recap about the optimal transport as also introduced in Minh talk. So what's here we just simply have a distribution of the bakery. We have 3 bakery, A, B, C, and 3 restaurant, X, Y, Z. We would like to transport donuts from the bakery into the restaurant. We have, in optimal transport, there are 2 main components. The first one is the cost metric. So it's the cost to move from the one donut process from the bakery to the restaurant. Here is the cost, and the transport plan is how much donut process which we remove. So it's just simply a linear programming. So we will minimize the total cost. The constraint here is the marginal constraint should be equal to the input measure, and the transport should be non-negative. So it's very simple for the optimal transport problem. As we know that to solve the linear programming is a supercubic able 3 log n with respect to the number of support for the input problem. At a special scale of the optimal transport, when support is on the line, we can imagine that if the bakery and the restaurant are on the same street, so we have that kind of situation. And for the 1D case, the optimal transport will have the closed form solution. F here is the cumulative distribution. So for example, here for the discrete case, we will sort the support from left to right and just start to move. Let's say here we have 30 to C, and we just move the donut boxes to the nearest one, to the corresponding Z here. And we still have 20 to move to the next one up Y and continue like that until the end. So we only need to pay n log n to sort the support from left to right. And it has a closed form solution. So it's very fast in computation. And it's also the reasons why people in machine learning utilize the slide washer style for application. Even though, as you can see, if we project the support in high dimensional into one dimension, we will lose the topological structure of the input measure. So here is the formal definition of the slide washer style. So here is the radial transform. So in some sense, we will bootstrap map a distribution in high dimension D into the line defined by theta. We will sampling the direction for the line. And the slide washer style is the integral of the optimal transport on each line. And in practice, we will use the Monte Carlo estimation for the integral. So we just sample some direction, just small number of direction. And for each direction, we have the closed form solution. So that's why it's very cheap to compute that kind of slide washer style. And we can use that for the as the loss function, especially in deep learning application, where people cannot use the optimal transport or even the entropic regularization, since it was still costly for computation. So here is the works of 6 years ago. So I start with the old one and try to motivate for the new one. So when we project support in high dimensional to low dimensional, we will lose the topological structure of the input measure. So one way to alleviate this issue is we try to explore the tree structure. So it provides us more degree of freedom to capture the topological feature. And the nice thing is it still has the closed form computation so it's still very fast for computation. So we have the closed form computation for the tree washer style. So we just change the cost. For example, if we would like to move from A to Z, we will follow the path here. So it will define the cost to move one donut boxes from A to Z. So it's just a tree metric. And by changing using tree metric at the ground cost, the optimal transport will obtain the closed form solution like this one. So it's sum over S in the tree. For example, if we consider this S, this SE, the WE here is just the length of that S or the weight of that S. And V is one of the nodes of the HE here, which follow the root. So VE is for that HE here. And gamma of VE is the subtree rooted at VE. And mu of gamma VE is the mass of mu in this subtree. So it has a closed form and quite fast for computation. But how can build the tree? Since for application, we don't have the tree as beforehand. So it is a well-known result in theoretical computer science where people call it the walk tree. So assume your data points in the hypercube. So that hypercube we can consider it a root node. And then by partition the hypercube into 4 parts, so we have the corresponding node. All of this point here represent for this node. All of this one represent for this one, corresponding his one for here. Here we still have many points, so with hierarchically partition the space, so we have more points, more nodes on the tree, and continue that until the end. So we can build the tree, use the tree metric for the tree washer style in application. However, for this partition-based approach, when the dimension is high, it will be exponential. So we can use the clustering at the remedy base for the tree matrix sampling. So we just consider the whole points at the root and give the cluster to partition the data points in a high-dimensional space. So it actually works, for example, in topological data analysis and document classification. The nice thing of the tree washer style is it's also positive definite kernel, unlike the optimal transport. The optimal transport is indefinite. So it may harm some application. For example, in topological data analysis here, it doesn't work well. But for document classification, it's work comparative to the tree washer style. And we can see that for the document classification, it's represent as for each work, it's represent as a 300 dimension vector. So the slide washer style is affected for its performance. And as you can see here, the tree washer style, the computation of the tree washer style and slide washer style compared to the standard optimal transport, it's very fast for computation compared with the standard optimal transport. But typically, that makes one of the reasons make the optimal transport popular in machine learning is it can use for deep learning. So before that, only a few people use optimal transport for application. But for slide washer style, the one dimension, it can use for GAN here for VAE and for diffusion model to generate images or documents. But for the tree slide washer style, there are no approach at all for generative model, even though we know that it generalizes the slide washer style. And we did try to use the tree washer style for generative model, but this doesn't work at all. So the challenge for the tree slide washer style, it will rebuild the tree like the walk tree or the clustering base. So for the tree, we have the finite number of nodes. In the line, even it's just a simple structure, but we can choose any points along the line. So it's an infinite points. But for the tree, if we just consider the node here, it's just a finite number of nodes. For example, if the node here, it can maybe many data points, maybe different data points, but it's in the same position in the tree. And it also have the discrete structure. So here, it's just the line is bounded by the two endpoints. And even for the tree, we cannot go further if we have the leaf here. So it limits the application of the tree slide washer style if we build like the walk tree. But for slide washer style, even it's very simple structure, but it doesn't have those kind of drawbacks. So very recent, we come up with once we call the tree system. So the idea is quite simple. So for the tree, each edge has a segment. So instead of using a segment, we will use the line to build the tree. For example, we have a system of K lines here, and it's connected together. If we add the tree structure, for example, the line 1 will connect to line 3, line 4, and line 5. So line 1, if you connect to 3, 4, 5, and 4, it will connect to 2, 4, it will connect to 2, and for this one, we call it the tree system. So we can address the drawbacks and can inherit some nice properties from the slide washer style, but still have more structure than the slide. So the line, we have the source here and the direction for the system of K lines. So it's just simply K lines here, and we need the tree structure here to build the tree system. And the new components for the optimal transport on with the tree system is we have some kind of splitting map. For example, for one support, it has the mass 0.6. We will project in each line in the system of lines, and it will split mass. For example, here X here is the mass is 0.6, and alpha is the splitting mass. And if it's splitting line 1/6, 3/6, and 2/6, we have for the first one, it will 0.1 for this projected corresponding points, and 0.3 for this one for the line 2, and 0.2 for the other. So then we can extend the radial transform for the slide washer style into the K lines. So the newest one is the splitting mass here. And for this one, instead of only one point, we have the source and the direction. It just changed a little bit here. The new thing comes from the splitting mass. And we can prove that the radial transform is still injective. The injectivity is important for application, since what we want is we would like to minimize the points in original space to measure in original space. Without the injectivity, if we minimize, let's say, the tree washer style in the projected space, if the cost go to 0, we don't know the original one, whether it go to 0 or not. So the injectivity guarantee for us, we can use the tree washer style, some kind of at the surrogate loss for the optimal transport. So here just the definition of we call this the tree slide washer style on system of lines. We just project into the system, push forward into the system of lines and compute the tree washer style. It has the closed form similar to the tree washer style like before. And in application, we still use the Monte Carlo for integral approximation by sampling K, for example, here L different tree systems. So from slide washer side to tree slide washer side on system of line. For the line, we will have one line and project the input measure onto that line. On the system of lines, we have K lines, and it connect with respect to some tree structure. And for each support, we will project to each line on the system of lines with the splitting mass mechanism. And then we still use the Monte Carlo approximation to deal with the integral in the definitions of the slide washer style and corresponding to slide washer style system of lines. However, for example, in the reverse one, if we have that support, if we project project on the system apply of the blue one, we have 0.4 and 0.6. Even we didn't consider the relative position between the support and the system applies. So by explore the Euclidean group invariance, so we would like to have something like this one. So if it's far, it's closer, so it's 0.3 and 0.7 if it's closer, and if it's farther, let's say 0.8 here and 0.2 here. So we would like to have incorporate the relative position between the support and the tree system. So this one properties we would like to have. The other ones is the Euclidean group invariance. So when it's it has some transformation, we would like the Euclidean distance preserved. So for the Euclidean group, ED is just a component of the translation group and the orthogonal group. So Q, so here is, for example, G belong to ED. We have here the translation, and Q is the orthogonal matrix, and I just the translation. And here is an example of the splitting mass satisfy the ED invariance. And here we extend into the other ways. So for the reverse one, we use the linear projection for the support into the line. Here we extend to nonlinear projection, and it's here. We call this there is corresponding ones for the circular radial transform for slide washer style. Here we just generalize it for the tree system. And similarly for the spatial radial transform, we define the other one. So typically it just try to map the support by the H function, and the H is injectivity continuous map. Typically just use the odd degree polynomial function. And the other ones is we can extend it for the distribution on the sphere. So here we need to build the tree system on the sphere. We leverage the stereographic projection for the sphere. So here is just two different perspectives. One on the hyperplane, go through the zero. For example, for this one, it will corresponding under the stereographic projection on the sphere like this one. And then we can build the spheral tree for the sphere. So the corresponding like this one. If we consider it's on the hyperplane going through zero, the x, and here the sphere. And then we also build the spheral radial transform for the spheral tree. And we also prove that it's injective. So it's satisfied for the application for generative model. And we apply it for denoising diffusion graph. So here is the work denoising diffusion graph. Here in the ICML 2024, we extend it to use the slide washer style for such kind of diffusion model. It's performed well. So here's several variants of the slide washer style. And here are some of our works. So here the original one with the three slide washer style on the system applies without anything. And here with the splitting mass correspond take into account the relative position between the support and the tree system. And the other ones is using the nonlinear projection And we also incorporate that kind of splitting map inside those kind of approach. Yeah, thank you for your attention.
Do you have any comments or question for the speaker?
It's very basic question. So tree structure, for example, number of branches and the depth. How do you determine the structure? From the data, can you determine the branch?
Yeah, we leave that kind of question for the future work. So here we just try to randomly sampling. So the other direction is we would like to try to learn the optimal one with respect to the given data. So here, yeah, it's one of the approaching the objective we would like to pursue in future. Yeah.
I see.
Yeah.
Thank you.
Thank you.
If not, we would like to thank the speaker again.
Yeah. Thank you.